प्रणाम सर। प्रोफेसर झा प्रणाम। Good afternoon, everyone. So we have 4 minutes. नमस्ते सर।
हाँ, नमस्ते शुक्ला जी, नमस्ते।
कैसे हैं सर?
बस बस बढ़िया है, बढ़िया। आप बताइए कैसे हैं?
बस अच्छा चल रहा है सर।
हाँ हाँ हाँ।
So participant Professor Jha sir has already joined here. So if you have any question based on his first lecture, then you can interact with him. We have 2 to 3 minutes left for the next lecture to start. So if you have any query or question based on his first lecture, so you may interact with him. Sir is available here.
Dr. Shukla, I will keep my video off because here it is raining, so the signal is, I mean, the connection is not that good. So I will keep my video off.
Okay, sir. No issue, sir.
Okay. Is my screen visible?
Yes, sir.
Okay, fine, fine, fine. So let me come to the.
Well, friends, so it's now 2 p.m. and it's time to start this session. Um, so let me begin with. Respected Professor Prafulla Jha, today's invited speaker, eminent scientist, Professor B.I. Sharma, head of the department, my dear colleagues and dear participants. I welcome you all in this fifth day of the workshop. Today is the last day of the workshop. And in the first very lecture by Professor Jha, he has already delivered one lecture on the foundation of the DFT, and Professor Jha will continue from where he left in the first day of his lecture. So, without wasting any time, I invite Professor Jha to deliver his lecture. Sir, please.
Thank you, Dr. Shukla, and good afternoon to you as well as Professor Sharma and all participants. Uh, anyway, this is Sunday with after heavy lunch, and let us see that how we can remain awake during the lecture, because I have to give only one, but you have to attend two, and then the valedictory function. So as I said that I will put my video off because weather in our city is not good, so therefore the internet connection is not that good. So I think this will provide better bandwidth. So I will put off the video, and then I will come to the slide. I hope you all can see my slide. This is with DFT. So I will start from here, but just briefly, I will in couple of minutes, I will just discuss or mention or just tell you that what we discussed in our previous lecture. Of course, that was the second lecture, in fact, you can say, because Professor Sen covered many things of the density functional theory and its development. And then, of course, later on, Dr. Jena also discussed the things which I discussed previously. But mine is basically in terms of foundation, where lots of equations and other things may appear. And not only that, because this is second last lecture of your workshop, and therefore I'm sure that you must have heard many things which I will be discussing or I will be telling you from different speakers, right? From the beginning, that is from Professor Sen's lecture, to the later on. But I saw the program and then at many places I observed that as far as foundation part is concerned, in fact, I try to cover, and then Professor Sen's lecture, in fact, the second which he delivered for the Weinberg-Kohn theorem. So I will not go for the proof and all the things of the Weinberg-Kohn theorem. Just only briefly, I will state the statements and its in a simple way, or maybe just its output, and then we will proceed for the exchange interactions, different types of exchange interactions, and then I will be taking some examples that how these exchange interactions are able to give you the different properties, right? So that is what is our focus, right? So as you know that in the Harty equation or the Harty approximation, of course, it was, you can say that after Born-Oppenheimer approximation, that was the first which considered the approximations to solve the many body problem, basically to bring the many body problem, many electron problem to the one electron problem. But there was two major shortcomings for the Harty equations, and that was that it includes the electron-electron interactions only in an average manner, right? And then the most importantly, that because we are dealing with the electron, so many body Harty wave function violate the anti-symmetric requirement. That means anti-symmetric nature, or that you can say that the Pauli exclusion principle was not included in the case of Harty approximation, and therefore in the next was the Harty-Fock approximation. And in the Harty-Fock approximation, this anti-symmetric nature of the wave function was introduced through the Slater determinant, right? And then basically it had the uh, term, if you remember, then it was having the usual Hartree term, then the kinetic energy operator term, and the last term, which was different from the Hartree, was basically due to the exchange, you can say. And this still has the problem, and the major problem with this, that means basically to the Hartree-Fock equation or Hartree-Fock approximation, was that it ignores Coulomb correlations between parallel spin electrons, which give rise to the exchange interaction, right? So this Coulomb correlation actually reduces the exchange interaction between the electrons and parallel spins, so that the Hartree-Fock equation greatly overestimates the importance of the exchange interaction, right? And in another word, if you say about the Hartree-Fock method, it's a mean field theory, right? Hartree-Fock method is a mean field theory. That is, the many body problem is reduced to one electron problem, in which the electron moves in an average field generated by other electrons. So these two were the basic development, we can say, as far as the many body problem, many electron problem was considered. That means basically the solution of the Schrodinger equation, right? Then the next problem with the Hartree-Fock, if you remember, I said that it is computationally costly, right? And that was the major issue, right? That means it is computationally costly because you know that wave functions which you have, that depends upon the coordinates x, y, z, and therefore if you have the large number of electrons, then naturally it increases the degree of freedom tremendously, and it is not easy to solve. And our purpose is what? Basically our purpose is to try to solve the many body problem by approximating the many body wave function, such as Hartree or Hartree-Fock wave method, as I said. And since the many body wave function involves the coordinates of all the electrons, that is, it is a function of 3n variables, where n is the number of electrons, right? And this approach becomes complex and numerically very demanding. That means basically it is computationally very costly. So if it would be much easier or much simpler if the electronic system could be described in terms of electron density, right? Which is a function of only three variables, x, y, and z. And a firm and exact theoretical foundation for such description, of course, was provided by Weinberg and Kohn in 1964. And that is basically known as the density functional theory. And we know that for this this achievement, the Walter Kohn was awarded Nobel Prize in 1998. But the issue is what, that we anyway here we could reach on a conclusion that if the density, I mean, if we could express the electronic system in terms of the density of course is an R, where R is the xyz. So this becomes density becomes the function of basically the position or coordinates, and finally the energy is the functional of position, basically density, right? So that was the all basic idea regarding this. And as I said that around that time only, when these developments were taking place, that means Hartree-Fock and all other, and then this drawback were observed. So at the same time, Thomas Fermi theory was developed. That means basically the concept which was to be introduced in the many body or many electron system by Weinberg and Kohn. That means in terms of density, that was at the same time almost. That means around 1927 by Thomas and Fermi, this thing was, or the energy density dependent energy was basically proposed. The basic, see, they were not developing the density functional theory, but basically their idea was to describe atoms, molecules, or solids in terms of electron density. right? And that basically will be coming shortly, right? Just prior to that, because now we are entering into the DFT, so we know, and you all must have studied or discussed in last several lectures. So just here there are some terminology like ab initio, first principle, all those things you know. The the slide, or in fact, this cannot be new for the participants or the persons who are attending a workshop on a DFT, that how popular is the DFT now, right? Because I will show you the example. In fact, I will tell you that what it can do, and maybe you might have also seen it, that it can do all sort of calculations, right, within its limitation. Limitation means that you have to select a proper exchange function, then maybe you have to have a good computing system, and of course you apart from that, of course you should have the expertise to handle the given package, right? So that right hand side, a graph is given that is for the number of publication with year, and you can see that how popular it is, right? In fact, yes, one of the paper based on DFT is that was published in the Physical Review later, is listed in top 10 cited papers, right? So that is how this thing is popular, and that is how why basically we all are here, right? So based after that, Harty-Fock, etc., we can say that the DFT is more accurate and precise than the Harty-Fock and post-Harty-Fock many body interaction model, right? It can be applied to anything, right? I will say that to anything in the material science to know any properties, right? And therefore, in fact, I work using density functional theory right from the drug design to the materials at extreme condition. That includes the materials inside the earth, that in the interior of the earth or the core of the, to the planetary material, right? So biomaterial to planetary material, you can say. That means that every where you will find its application, right? And in fact, it is not an area which only material scientists can, or the condensed matter physicists can use basically. Now it is, I have seen the papers that come in the field of nuclear physics. Of course, this theory is in, as I said, in the planetary materials, and therefore wherever the materials comes, this density functional theory is applicable, and that is why it has wide range of applications, right? I have listed some and given some figures that it applies to atoms, molecules, surfaces, and periodic structures. You can find the ground state energies basically. You can have forces, stresses. See, the forces, stresses are very important, right? I don't know how many of you basically calculate the thermal conductivity, right, of the material, right? There you basically you have to go the second order, third order, fourth order force constants to have the proper convergence, right? Then you can do the structural optimization. That means the parameters you'll obtain for a given structure, and which can be directly compared with the X-ray diffraction or the neutron diffraction data. Elastic constants, right? Elastic constants are basically you can say that this is the part of the mechanical properties of the solids, or the mechanical properties of the material, and therefore it has wide application. That means it has large number of application when it comes to the engineering branches, right? That means people do the mechanical properties studies. Of course, the code is known as elastic code, which is many of you might be knowing. So elastic modulus, you can calculate the elastic constant and many properties which are driven from the elastic constants, right? Electron band structure of many body systems, of course, that is the primary thing. Phonon frequencies and eigenvectors at any wave vector, right? Again, this phonon calculation, right, is very important, right? Because it does not give only the properties associated with the thermal and many other. But in a recent years, right, if you see the papers, particularly on the two-dimensional materials, referees, or maybe you have yourself will try to do that, you will do the phonon dispersion call calculation, and to basically to show whether phonon dispersion curves of that material in a Brillouin zone has all real frequencies, right? That means having real frequency in the whole Brillouin zone is basically confirms the dynamical stability of the material, and therefore you will see that this has become very popular, right? To show the phonon dispersion curve in context of the stability in two-dimensional materials, and you will see that people report it. I have seen that people reporting even with some negative frequencies, which is of course not correct, but with some justification, that is calculational error, etc. People. So phonon frequencies, eigenvectors at any wave vector has become very important. As I said, that full phonon dispersion to show the dynamical stability, to know the behavior of the phonon modes in the whole Brillouin zone. You can have the electron phonon interactions, right, to find out the superconductive temperature, right? As I was mentioning the thermal conductivity, so you can use the electron phonon methods to calculate the thermal conductivity of the system, and then of course finally the ab initio MD, right? That means in a simple word, even you can derive many characteristics, many properties, but one thing is important, as I said, that with time, with temperature, people try to show the stability of the system, right? So what is basically the DFT, right? So DFT is a formally exact representation of the n electron Schrodinger equation, right? You all must be remembering from where we basically started. See, this is in the left panel, left side, you have the Schrodinger view. That means you can see here, this is exact potential, right? And here the electrons are there. Those electrons basically interact in the presence of external potential, you can say, right? And these are basically the interaction, electron interaction. This is red balls are electron. Then this basically shows this complex or the complicated interaction, and then this is the external potential, or you say basically this is what is the actual potential in which one has to solve, right? This can be made formally equivalent with the approximations, right, like this. So here the electrons are non-interacting, right? So this is basically the quantum particle, and this becomes the effective potential, right? We will see that what it is, how this effective potential is achieved, right? But that is what is the you can say that approximation of Schrodinger view, right, or Schrodinger equation, many body Schrodinger equation comes in this way. So this is Schrodinger view, and the right hand side you have the DFT view basically, right? So this is the ladder, right? Just I was mentioning that how basically the DFT DFT progressed. So Gilliam model, Thomas Fermi model, Hartree method, modified Hartree method, Weinberg-Kohn theorem, and basically that is what is in 1998 you have the Nobel Prize to Walter Kohn particularly in chemistry for this density functional theory development. But beyond that, after 1998 or maybe prior to that, after discovery of density functional theory, it has reached to a very high level, right? High level means that means it has great applications, right? And to predict the properties or maybe to confirm the properties, and a lot of activities are basically being done in the case of the field of density functional theory. That is what it is there. Now I will come to the Thomas Fermi model, because that was the point, right? That is how the density come into the picture. How basically the Weinberg cone realized how basically they combined that the energy can be expressed in terms of the density. So for that, the Thomas Fermi model was developed. It was first to use the electron density as a basic variable, and basically, as I have told you just now, that the basic idea is to describe atoms, molecules, or solids in terms of electron density, right? So, of course, I will not show you here that all the steps of the derivant, but major parts will be there. Basically, my intention is what my intentions are two. One, that is how basically the concept of density functional the density comes into the picture. That is one thing, and that is what I was telling you, that Thomas Fermi basically gave this concept that the energy can be expressed in terms of the density. And then of course the another thing is that the simultaneously many people work in different areas, and then one can take the help of results from of one another to develop a particular theory. And that is what happened when you had the Hartree-Fock equation, right? Hartree-Fock methods, because in the Hartree-Fock methods, the antisymmetric nature of the wave function was included based on the Slater's determinant, right? So simultaneously, some other works are also being done, which was basically helpful for the development of this. See, basically what that kinetic, because these few things which what we have written here, that you can find it in the Ashcraft, Mermin, or any good solid state physics book. But let us consider a homogeneous electron gas of volume omega containing L electron. So N0 is electron density, let us consider. Kinetic energy T can be expressed by this expression. And if you go for the kinetic energy density, you can see that the T0 is expressed with this term. And here on the right side, on the most right side, you have a term that is N0 to the power 5/3. That means how the kinetic energy density depends upon the electron density. That was the first thing. Then we can come to some real system that we know that electron density is not homogeneous but inhomogeneous. But Thomas Fermi theory uses the results of homogeneous gas, and it assumes that it is uniform locally. Right? So this is how basically you can see that NR, that is density, is given by this, and energy, kinetic energy basically is given by this expression. Ck is a constant. I have not written here, but anyway, Ck is a constant, has several terms. So you can see here that how it depends upon the Nr, that is on the density. So total energy will be like this, and you can see that in each term, right? In each term, that means basically the term associated with the kinetic energy term associated with the ion electron interaction, and the term is, this is what is basically the Coulomb, right? Here we are not talking about the classical electron interaction and exchange correlation energy. Just to have an idea that how density was important, and how all the terms from the total energy was expressed in terms of the density, right? And after solving these things, that means with that when the energy was minimized, right, with a constraint that the total number of electron is constant, then the minimization was done, and finally we obtain an expression mu. Normally when we derive, then we say it is mu is nothing but a Lagrangian multiplier, but finally it is what it comes as chemical potential. So mu is given by this, and the point is that you see that it depends upon the density. So this is basic equation of the Thomas Fermi theory, the equation which is extremely simple to solve. The equation is in terms of, right, electron density, which depends on R, right? So point is what? The point is what? That the Thomas Fermi model basically, or the method basically, gave the idea that how energy of the system can be expressed in terms of the density. And the advantage of using density will be what? That it depends only on three coordinates, x, y, and z, right? And therefore it reduces. Now, we have, in fact, I should not spend much time on this, but I will simply just state to have the continuity, right? So you can see here that there are two theorems, and the external potential VR is a unique functional of the electron density, right? As a result, the total ground state energy E of any system is also unique functional of N, R, that is density. And the second is the functional En of the total energy has a minimum equal to that ground state energy at ground state density, right? So these are the two theorems, and I'm sure that you have been told very nicely about this by Professor Sen, and also you must have seen the derivation, right? So from the first theorem, right, what is the output, what is the outcome, that from the first theorem, electron density Nr associated with the ground state corresponding to an external potential Vr cannot be reproduced by the ground state density corresponding to different VR, right? So basically this is what that means. It is uniquely representing, right? That means what? That means you cannot have one set of, right, electron density with the help of different potential, right? So that means the potential VR is uniquely representing NR. That is what basically. And then the second one, this follows that the ground state electron density NR determine VR uniquely, right? That means basically, then what? If VR is unique, that means the NR will give you the unique Hamiltonian, right? So that is what is the idea. And based on that, you had this ground state energy E can be written as this way. And here you have the three terms: kinetic energy term, classical Coulomb term, exchange core. You will have this term in when we do the, right? Oh, sorry. Right, then you have the next is the Kohn-Sham equation, right? So this equation is to be solved, right? That means you have to, you can see here that all the terms are there. Thus it would give us the electron density Nr, which in turn would give us the total energy. That means you have to minimize this with respect to the density. But there are two problems. One, that is the functional Tsn is not known, and the second, V exchange is also not known, right? So the Kohn and Sham basically introduced the concept of orbitals in the DFT, right? They introduced the orbitals in the DFT, and they noted that the E exchange was absent. Then the expression would be identical to Hartree expression for energy. The V exchange R would be absent in above equation and can be solved by using, and finally, this NR is equal to this, and finally psi of IR can be obtained by solving this equation, right? Here you can see that this is a usual Hamiltonian, you can say. H psi is equal to, right? H psi is equal to E psi, right? Where this term is common here, this is V effective, right? That means basically the total potential which you have is combined with V of R, VH of R, that means Hati, and the exchange, that is XCR, right? And here you can see that it is this equation is known as Kahn-Sam equation, and psi IR, EI, and V effective as quantum orbital, quantum energies, quantum potential respectively, right? So the basic most important aspect of the quantum equation was what? That they introduced the orbitals in the DFT. And finally, with simplification, this equation was obtained. And in this equation, you have a usual um, uh, Schrodinger equation, right? It is similar to the Schrodinger equation with effective potential as V effective, right? Now, as I said, that the most important and the difficult part is basically to have this exchange interaction, right? And for that, the many approx. See, अब क्या है now what we have, that now we have to only basically solve this equation, right? And it seems at least simple. Of course, it is not simple. It is not easy to solve, right? But at least it looks simple now, right? And to have this, that means basically to have the solution, that is V exchange, right? Because accuracy of this equation, accuracy of the solution of this equation basically very much depends on the exchange, right? That means what kind of exchange you are basically including in this, right? And for that, the simplest approximation, simplest exchange that was considered was the local density approximation, right? And I remember that Professor Sen mentioned in his overview lecture, but he might have also explained, many people might have explained you, but this is what is the exchange, and that is a very important aspect. And for this is not easy, right? And therefore you require the approximation for this itself, and or maybe the many different forms, right? Here I am sure that many exchange interactions would not have been discussed, and I will try to cover at least most of them, at least those which are very popular, right? And the most popular, or the first one that is most popular, is the local density approximation, because it is simple. One thing, it was developed by the quantum themselves, right? And therefore it was the first one. And oh, sorry, this right. Right. So the first one was the local density approximations, right? So it contains the information on the many body system of interacting electrons. The easiest, as I said, is the local density approximation. What does it consider? It assumes that the functional is the same as a model problem. That means the homogeneous electron gas. Separate the exchange and correlation contribution. So EX is exchange, EC is the right, and EXC, exchange energy, can be calculated as a function of the density only, and that is what. So assumption is made that EXC depends locally on rho r, which is density, and EXC LDA, if you do the integration of this, and that is basically rho of r, EXC homogeneous r dA. That means you can basically say that you have this rho r, and then you have the E exchange homogeneous r, right? When you have the interaction, I will show you something different while discussing that how density comes. So that was recommended by Purdue Wang in 1992, and LDA is currently being used to study fundamental problems in physics, chemistry, geology, material science, and pharmacy. Why? Because as I said, that this is simple, right? And of course, it is not 100% correct. It has the limitations, but when you are not interested in an accurate value of anything, that you are interested in trends, right? Then this is excellent, because it is simplest, right? And less computationally less costly, and therefore this is most popular, and the most of the calculations are basically done by using this only, right? So this is what it is, right? This was basically what I was telling you, that LDA in homogeneous electron gas. This is rho R, EXC rho R dr. So this means the probability of finding the particle at R, and this is what exchange rho of R dr, a homogeneous electron gas exchange correlation energy per particle, right? And that is what it comes. And you can see that the value of exchange energy depends only on the local density, right? The electron density rho may vary as a function of R, but rho is single valued, and the fluctuations in the rho away from position R do not affect the value of EXE at R, right? So my mouse is moving, right? So what does it do? In a nutshell, local density approximations. This is what is the expression for that, how this E exchange for LDA is obtained. So it is local dependence on density, right? Or Wigner-Scheidt radius, and that is given by this. Exchange energy per electron is that of the homogeneous electron gas. Exchange part known analytically. Correlation part is also known analytical for Rs tends to 0 and Rs tends to infinity, that is Wigner-Scheidt radius. Numerically exact for Rs lying between 2 to 100 from quantum Monte Carlo data, as parameterization interpolating over Rs, right? Workhorse in DFT application to solids, right? In fact, as I said, that's the most popular one. Real systems are far from Gilliam-like homogeneity, right? And we have to see that why does LDA work at all? Where does it fail? How to improve beyond it, right? And now I will tell you that it's regarding the performance. That is a very important part, right? Many of you might have seen, right? At least now it is there or not, but sometimes back it was there, that when you report your results with the LDA, the reviewer will ask why LDA. If you are going with the GGA, then why GGA? Or in many papers, you might have seen that people justifying the results of LDA and the GGA based on their performances, right? So you see that what are those things by using LDA, right? And as I said, that this is simple and the most easy and computationally less costly. Therefore, most of the people basically use it, right? And you remember one thing, right? Sometimes it comes as a statement that what is the failure of DFT? Then basically people tells that, okay, the band gap is not predicted or the calculated properly, right? So, but if you want to have the band gap, then it is fine, right? But if you want to have only the trend, that is how the band gap basically varies for different systems, then there is no need to go for other kind of functionals, because that will be costly, that will take much time. You require a big computing system, and therefore it is you can start your calculation by using the LDA itself, right? So structural, elastic, and the vibrational property. Vibrational properties mean that is the phonon, and finally you can say that Raman spectra or IR spectra are often good enough. Crystal bulk lattice constants accurate to within 3%, right? Or so you take a statement as this, it is underestimated. Bulk modulus somewhat too large, right? And greater than 10% error, not uncommon for D metals. So it's using D metals or D band systems are difficult, but anyway, the bulk modulus are large. Crystal lattice constant is less. Underestimated, bulk modulus is overestimated. I remember the early calculations of the DST and sorry DFT. These things were very common that okay our results on the lattice constant is underestimated from the experiment, so that is a drawback of LDA. Bulk modulus is overestimated, that is also the drawback of LDA. Right, phonons somewhat too stiff, that means frequencies are higher. Binding energies are too negative, right, that means basically the overbinding takes place. Cohesive energies of the solids, but formation enthalpies okay. Molecular optimization energies, that is the mean error, is around -3 electron volt. Activation energy in chemical reaction unreliable. Too small, too absent, that means example for H2 on various surfaces. Relative stability of crystal bulk phase can be uncertain, right? And the examples are SiO2, a high pressure phase, more stable than the zero pressure phase, right? That means more stable, that means energy is less, right? Underestimated transition pressure. Example for diamond to beta tin phase in silicon and germanium, right? So the transition pressure is underestimated. Electronic structure can be usefully interpreted except for band gaps, right? That means, as I said, that band gap is not predicted correctly, right? Beyond LDA, right? What are the different things which we basically can have from beyond LDA? So just I list here and then we will go one by one, maybe not all, but many of them. So beyond LDA, that means LDA is based on the homogeneities. So in homogeneities in the density, self-interaction cancellation, non-locality in exchange and correlation, strong local correlations. Then you have the gradient expansions, weighted density approximation, exact exchange in DFT, right? DFT, Hartree-Fock hybrids, right? These are the different self-interaction correction, van der Waals and RPA functionals. Then you have the LSDA plus U, you can have the LDA plus U, you can have the GGA plus U and all the multi-reference quantum and the GW approximation, right? GW. So at least some of you might be aware, see GGA, LDA, GGA is known to everybody, right? Then the correction comes, that is in terms of U. Sorry, then you will have the spin polarized calculation. So LSDA, GSDA, then you have the U correction to that. And the major part basically comes for the actual correct value for that is hybrid. Hybrid is basically the combination with the LDA plus Hartree contribution. Then you have the GW approximation, which is very much popular in the case of semiconductor, where you have to go for the band gap, right? So here I have just mentioned, and I will go. See, we have the local spin density approximation. So you have here the up and the down spin both. That means when you want to know the magnetic properties of the system, you have to perform the spin density, spin polarization calculation. Similarly, for the generalized gradient approximation, generalized spin gradient approximation, right? So these are right. So LDA and LSDA. LSDA is what? LSDA is basically the in spin polarized calculation, right? So approximation as far as exchange is concerned, it is same as in the case of local density approximation. So what does it do? It favors more homogeneous electron densities, overbinds molecules and solids. So these are the drawbacks of LDA. Geometries, bond lengths, angles, vibrational frequencies reproduced within 23%. So it is again drawback. Dielectric constants overestimated by 10%. Bond length too short for weakly bound system, that is for the hydrogen bonded system, or maybe the van der Waal interaction, or the layered structure, you can say. Correct chemical trains. Atoms, that means score electrons poorly described, right? And in that case, HF Hartree-Fock is better. Exchange potential decays exponentially into vacuum region. It should decay as minus E square by R, hence it is poor for dissociation and ionization, poor for metallic surfaces and Fiji absorption, very poor for negatively charged ions, right? Poor for weakly bound systems, just it is repeated. Band gap in semiconductors are predicted about 40% less, poor for strong on-site correlation. That means basically the systems having the D and F cell unfilled systems, right? That is right. Now let us see that how basically the GGA compares with the LDA. So atomic and molecular energies are improved, right? GGA corrects the LDA over binding, right? So these are some examples you can see. Better cohesive energies of the solid. GGA softens the bonds, increasing the lattice constant, decreasing the bulk modulus, right? There you have seen that drawback of LDA was what? That LDA used to give the underestimate the lattice constant, and overestimates the bulk modulus. So the GGA basically does not do that. It does the reverse. So LDA yields good relative bond energies, for highly coordinated atoms. GGA favors lower coordination, not always enough where LDA has a problem. That means basically CA absorption sites on transition metal surfaces, significance of GGA, right? GGA work function for several metals turn out somewhat smaller than the LDA. One particle energies band closest to LDA, van der Waal dispersion or van der Waal forces are not included, right? Just here I have given you the example, right? Anyway, this is from our paper only, just to tell you that how the LDA, GGA, and LDA plus U basically results, right? So comparison of LDA, GGA for structural and electronic properties. Now here you can see this is a HCO, basically you can say it is a delafosite compound. So here you see that I will just take the last energy. LDA gives you 1.28, GA 2.86, and if you have the LDA plus U, then it is 2.02, and experiment is 2.0, right? So here I would like to tell you one thing, that a quality calculation is what, right? Quality calculation is basically it can be understood in two ways. One, that if you are predicting, right, then you do all sort of calculations, right? That means you do LDA, GGA, LDA plus U. If you have the G semiconductor insulator, then do the GW. If you have the hybrid, you want to use hybrid, you use the hybrid functional. So that you will have the range of values, right? So if somebody, some person, some industry wants to have the values of band gap for a certain system, then you have to calculate and leave the thing. But if there is experimental data available, then naturally you have some sort of guidance, right? That means you do the LDA, you do the GGA, you do the LDA plus U, or maybe GW, or maybe etc., and then you see that which exchange or the which calculation basically gives you the correct value of the experimental data. But if there is no experimental data, if you are trying to predict, then naturally you'll have to, you should perform the calculations with several exchanges, right? Just here, I will show you that structural parameters at high pressure using different functionals, right? So what we have done, we have calculated the V by V0 that is normalized volume for COOH2 using different functionals. Results are compared with available experimental data. Uh, Many lines are there, right? So you can see that you have done PBE plus U, we have done PBE sol plus U, PBE sol, PBE LDA, and then we try to. Here you can see that LDA, PBE plus U, and the PBE sol gives better results as compared to the simple PBE functional. That means the green line, right? Similarly, if you go for the lattice constant C, let us consider. So calculated pressure dependent lattice constant using DFT and DFT plus van der Waal, right? Results are compared with available experimental data, and you can see that inclusion of van der Waal correction significantly improve the result, right? Anyway, because in this case I had the data, synchrotron data for pressure dependent lattice or pressure dependent structural parameter. That is why we could do. But we have done calculations for almost, not only here I have written 4 5, but for many combinations. So point is what, that you have to select, take a proper exchange correlations in such a way so that it gives you the very close value to the experiment or one, or if if you are predicting, then you as well as others should have the confidence in the data. Right now, beyond GGA, right, orbital dependent exchange functionals, right? So I will leave this and then I will directly come to hybrid functional. See, what is hybrid functional, right? So it is mixing exact exchange with LDA and GG. That means here you must have seen, right? I don't know whether anybody of you has faced this or not. That means if you are taking a hybrid functionals, then you have to mention that how much percentage of the Hardy was included. So hybrid functional means, that means you have the LDA, GGA, and you are adding a certain percentage of Hardy, and that is how it becomes the and that is what basically we are trying to say. So exchange is what? EXS plus LDA correlation is less accurate than exchange. Challenges: correlation functional that is compatible with exact exchange. Hybrid functional to interpolate adiabatic connection, right? So you can see from this particular diagram, right? And here that means on this end, right? So basically that both LDA, GGA are good, and while in that case LDA, GGA is quite negative, right? So hybrid functional, how they are defined basically. So use exact exchange for lambda, basically local functional for lambda. Hybrid functional is basically expressed in this way, right? So mixing parameter is alpha, right? And this is important. One has to tell that is what is the mixing parameter, and that is basically a control with the person who is performing the calculation, right? And here you can see that PBE, PV0, and then what was the exact value. Now here let us see in this case, energy gap is calculated by GGA plus HSU functional, and here EG calculated by the GG, and you can see that how the band gap is basically tuned. In this case, if you say that energy gap, direct energy gap is which is 4.81 electron volt. In the case of GGA, basically is 3.3 electron volt. And here from this to this, that is indirect band gap, which is 4.4 electron volt, reduces to 2.81 electron volt. This is on the left hand side. We have the phonon dispersion calculation together with the phonon density of states, right? What I was mentioning in the beginning, that what you can get several information, at least one information which I was mentioning, that is the real frequency. You can see in that in this brilliant zone, right? You don't have any phonon modes which uh, has the negative frequencies, right? And this not having the negative frequencies basically tells us that the system is dynamically stable, right? Dynamically stable means what? That means if you remember the system, that is we start with f is equal to minus kx. That means in the case of harmonic approximations, f is equal to minus kx, and this is basically a force that is of a restoring kind of restoring force, right? That means having the negative phonon frequencies, right, means there is no restoring force, right? And if there will be no restoring force, you can say that okay, there will be no harmonic motion to that, right? That means there will be and that is what basically it tells that there is no restoring force, and the phonon modes are frequency of the phonon mode is negative. That means basically the system is dynamically unstable, right? In fact, it is not the global minima, right? You remember it is a local minima only, but it tells about, at least at the first hand, that the frequencies are positive or not, right? So highlights LDA and the GGA are de facto controlled approximations to average exchange hole. GGA remedies LDA shortcomings, still can and should check GGA induced correction for plausible by simple arguments like homogeneity and coordinations. Hybrid functionals basically mix in exact exchange, orbital dependent implicit density functional. Always tell what exchange functional you have used it for your calculation. Example, PBE GGA, not simply the GGA, and helps others to understand your results, right? Helps to see where exchange functionals do well or have a problem, right? So DFT is a description of interacting electrons in the ground state, including exchange and correlation. The basic variable is the density rather than the wave function. The theory is simple and the implementations efficient compared with other methods. Implementations scale at least as well as n to the power 2, right? And in fact, with respect to the basis set also that Professor Sen in fact discussed, it offers an excellent balance between accuracy and scale of the calculation, right? This is how the self-consistent process, that is quantum energy, is. See, we start with the initial case, right? So V exchange is unknown, and for that some approximations such as local density or the GGA are considered, right? And we perform this calculation self-consistently, and you can see from this flow chart, right? That means till the new density is equal to the old density, the calculation is repeated, right? There is a term which is basically the pseudo potential. So job of the pseudo potential is what? To replace complicated effect of non-valence electron and nucleus with effective potential, as you can see from this diagram, right? This is basically the all electron wave function, right? And what you take, that is, this is what is the pseudo potential, right? And this is also, so basically what does it do? It is just an approximate, you can say, that is potential, or rather it replaces the complicated potential. There are two types, norm conserving and ultra soft, right? And then the success and failure of standard DFT in solids. The standard LDA GGA gives good description of structure and electronic properties of most solids, as I have said. Problems with the localized electrons, late 3D transition metal oxides and halides. They basically show the metallic behavior instead of insulators. Then the 4F and the 5. See, these are of course some problem, but people, or in fact, one can do with the hybrid functionals, or uh, maybe with the inclusion of the U. Normally people do it, right? For instance, weakly correlated electron FeAl is ferromagnetic in theory, but non-magnetic experimentally. 3D band position, that is exchange splitting, right? uh, I will, right? I, uh, should go or not for this. See, this is just talking about the phonon calculation, right? That is vibrational experiments, right? You know that most simple and the easiest experimental or popular experimental techniques for vibrational spectroscopy is neutron scattering, infrared spectroscopy, Raman spectroscopy, and all other. And therefore, the theoretical calculation of vibrational mode frequencies and intensities from first principle is very helpful in analyzing the vibrational spectra. That means the phonon dispersion curve anyway we calculate, but we can also calculate the Raman spectra as well as the IR spectra using this, right? So I will not go into the all details of this calculation, because this is available in the book, but wherever it will come, that I will discuss, right? Let us see that. Practical calculation of vibrational mode. So common methods based on DFT theory to calculate vibrational modes, that is via interatomic force constant, is what? That is one technique is frozen phonon technique, that uses the finite differentiation of forces, right? So that in some of the codes you will see that the phonon calculations are done by using the finite differentiation of forces, or basically the phonon frozen phonon technique. I don't know whether you have seen, there was a code, perhaps the phonopy or the phonon, by some group Polish scientists. I don't remember exactly now, right? But most of the people, and particularly even one who does uses the quantum espresso code, use the density functional perturbation theory, and that basically gives the direct calculation of second order derivative of the energy, right? So by using the density functional perturbation theory, you can calculate the phonon modes, full phonon dispersion curve, and then of course for the Raman and the infrared spectra. Then using interatomic force constant, also it can be calculated. That means basically by using the molecular dynamics simulation, right? So MD, that is can be extracted from the molecular dynamics runs via the Fourier transform of the velocity autocorrelation function, right? If anybody has some idea about the molecular dynamics simulation, can immediately recognize that when you have the velocity autocorrelation function, so you have the velocity autocorrelation function, and by taking the Fourier transform of that, you obtain the frequency, right? So basically in this case, the whole density of a state is plotted, right, or obtained, and that also gives an information about the stability on many other. So, or yeah, FW has the peaks at the vibrational frequency, right? So you have the whole spectra, and at FW you will be having a peak, and that is how it is, right? So I will not go into the how to calculate the phonon calculations, spectra, sorry, but in this slide, or in this presentation, everything is there. I will send it to Dr. Shukla, and if any of you want, you can just take it, right? And with the help of this, you can find your I mean, the complete aspects of this, right? Calculation of interatomic force constant, as I said, is very important, mainly when you want to go for several properties like nowadays, basically in terms of the electron phonon interaction, that is one thing, and when you go for the thermal conductivity, and right. So uh, this is calculation of linear response, right? And this is some of the figures I will be showing from our own calculations, that this phonon dispersion curves are representing 5 different models of graphene dioxide, and in some of them you'll be finding that the lower phonon modes, particularly in this, or maybe in some here also, you can find out that some negative frequency is there, right? So just I have put this to show you that you can have the different models, and for a particular material, here it was a graphene dioxide, and we have obtained the phonon dispersion curve for this, right? These all methods are given here to calculate the infrared cross section, then infrared spectra. Similarly, you can calculate the Raman spectra and all other. So all theories are basically given here. I don't know whether you people have interest in this side or not, but if you have, then you can take it from here, and or you can write me if you have any problem in this. I can certainly help you, right, in learning all these things, because it is through the online also, right? In fact, when I prepared that time, I have prepared that practical phonon call calculation in quantum espresso code. And when I was going through a program, I saw that a couple of lectures perhaps is based on this quantum espresso code. But I don't know whether that phonon calculation will be done or not. So just briefly I mentioned, and if anybody has any problem, right, you can write me, right, and I will certainly be happy to help, or do the calculation for you if it is required. Otherwise, just I will tell you how to do it, right? So SCF calculation at equilibrium position, that is performed by PWX, you know it. Single phonon calculation at finite wave vector, right? So that is basically the code PHX, right? So it single phonon calculation and gamma vector. So calculate CQ, diagonalize, produces. So basically it is the code that is the PHX, right? And then it gives all related, right? Just you remember, when you want to have the phonon, Raman spectra out of this phonon calculation, you should put this tag L Raman as true, right? Similarly, so these are the option, that is for polar materials, you should give the ipsil, that is dot true, to PHX file, right? So impose acoustic sum rule, add the non-analytical LO splitting, calculate cross-section if data is available. That means by using the code dynmat.x. So these are all related to phonons only, right? So because I know now many people know the basic calculations by using the quantum espresso and at least the VASP code. So you can calculate the phase transition, right, of any compounds. Here I have taken asymmetric delta ALF, right? It is so Raman. We calculated Raman spectra for at 0 GPa, 5 GPa, and the 15 GPa, and at 5 GPa, right? Sorry, 0 GPa. You can see that these two peaks are very prominent, right? When you go to the 5 GPa, these two peaks become shorter, and finally at 15 GPa, this peak disappears, right? This peak disappears, and the X-ray data or other data basically supports that at around 15 GPa, there is a structural phase transition for delta ALOH going from P21 NM structure to the PNNM structure. So by using the phonon calculation, by using the Raman spectra, IR spectra, you can basically predict or confirm the phase transition in the solid, right? Uh, right. So this is steps are given, right? Anybody has the interest, you can go through these steps and calculate, right? I will take another example right here, that computational Raman spectra for HCO2 polytypes. So without going into that, I will just say simply that it exists in two phases, the 2H phase and the 3S phase. And space groups are given for both 2H hexagonal and 3R rhombohedral. And you can see here, right, that with pressure, there is a shift in the peak position, right? And in here, right? And in the 3R phase, you can see that there were two peaks, right? But going to around 45 GPa or so, that other peaks basically completely disappears, right? So these are the basically indication of the transformation or the phase transition occurring in the different but the point here is what, that by using the density functional theory, you can calculate the Raman spectra, you can calculate the IR spectra, you can calculate the phonon dispersion curve, therefore you can calculate the electron phonon interaction. If you know the electron phonon interaction, you can calculate the superconducting temperature. Not only that, you can have a separate approach based on electron phonon interaction for the determination of thermal conductivity, which is a very important aspect of today's thermoelectric materials design, right? This is what optical properties can be calculated, right? Then this is basically working of toxic gas sensors, but you don't go into the detail, just to remember that you can understand the interaction mechanism between a material and a gas molecule or the biomolecule or any other two materials, right? So you can have the interaction mechanism understand, and based on that you can design whatever you want, whether you want to design a sensor, you can want to design or maybe you want to design a catalytic material, right? So this was basically, we have applied it to the toxic gas sensor. So as I said, that there is a tuning of band gap, right? And through tuning of the band gap, other properties will be tuned, such as work function, etc. And one can say about its use in for the gas sensor also, right? This is another method. Those who are from the physical chemistry can realize that reaction coordinates can be calculated by using the NEV method, right? So you can have the reaction coordinate. That means basically it is useful when you have a system that suppose you have the two salt or two things, and after the reaction, which is possible or which is not possible, right? And so that kind of things are basically possible with this. Then you can calculate the solar parameters. That means basically the parameters which are useful for the solar cell, or basically, if in a fancy word, if you say, we can say that we can design the solar energy material, right? And we have done it for MAPI, that is methyl CH3 lead iodide, right? That is one of the most popular material for solar cell nowadays. So it has the three-dimensional structure, two-dimensional, one-dimensional structure, and we in fact studied its parameter, right? That means all solar cell parameters by using the first principle calculation. That means basically the electron structure calculation. Those who are working in the solar cell can immediately see that these are the parameter JSC, J0, VOC, fill factor, solar efficiency, etc. Everything we can calculate by using this method, right? So I stop here, and if anybody has some questions, I will be happy to answer. Right? Or still anybody has a problem, you can write me uh, on my mail. If some anybody has any problem, or you want to learn something, right? You are most welcome, right? And my group will certainly help you in doing that, right? So thank you very much. I am waiting for questions. If you have any, please.
Yeah, thank you, sir. Now, participants, you may ask a question. You may unmute yourself and ask question. If you have any question,
Hello, hello.
yes,
Yes,
Pramod.
hello.
Yeah.
Yes, hello.
Sir, I have one question regarding the reaction coordinates. Sir.
Yes.
S-
Tell me.
Sir, in reaction coordinate, while calculating the transition states, we
Yeah.
get one imaginary frequency.
Huh.
So, what should be the minimum, like for the transition states, one negative imaginary frequency we get? So, my question is, what should be the minimum uh, energy frequency, value of frequency, so that we can confirm that okay, this is the uh, transition states. Is there
No.
any?
Yes. Your problem is basically you are getting the imaginary phonon in energy. Sorry, negative energy, right?
Yeah, that is required for the confirmation of uh, transition states. But my question is, what should be the minimum value of that frequency? Is this, it should be less than 100 or it should be above 100?
See, it depends upon the system, in fact. But if it is less than 100, it is good.
Okay.
And can I add something here,
Yes,
Yes, sir.
yes.
Yes.
Professor Jha? So, Pramodji, actually, you have to sometimes you get the negative frequency and you believe that this is the actual transition state. But the
Yes, sir.
main thing should be that you have to visualize that the in which direction the forces are, and if it's in the same direction where you are expecting your product to be, then only
Yes,
you
sir.
will designate that transition state as a real transition state for your product. Sometimes it's just a different way. I mean, some in opposite direction you will be getting forces and the system will not be, I mean, what you are expecting
Yes.
as a product.
Yes, like my question was like if I'm searching the transition state for that reaction only, but my value is less, can I consider that as a
I, th-
transition state? Like
I, I,
if it is
I,
around 50 to
I,
60.
I think so. I think so.
Yes, yes.
No problem at all.
Okay, sir. Thank you. Thank you, sir.
Yeah, Utpal Sarkar has a question.
Actually, not a question, sir. Actually, the question, the previous question was how much the value of the frequency most probably Pramod is asking. So
No, energy or frequency?
it is the value of the frequency, right? It is the value of the
Yes, sir.
frequency to know whether it is
Yes, sir. Yes, sir.
yeah. So what I have seen is that up to 10 centimeter inverse, if you find minus 10 centimeter inverse, then you can you may avoid it. But if it is beyond 10 centimeter inverse negative, of course, then it's basically a negative frequency. And how much value you will get is definitely the steepness of that potential energy surface. It's basically the second order derivative. So whether it is if the potential energy surface is very steep, then you will get definitely high values, and if it's flat, then it's basically a small value you will get.
No, no,
Thank you, sir.
I will add one more thing. See, anyway, remember one thing, the negative frequency is unphysical. So there is no doubt that what values. Normally what happens, why we accept up to 10 or 15 or 5, etc., that if you increase the computational accuracy, right, that means basically the tolerance, and which in fact become the costly calculation, and that is why we do not go. So we accept, okay, 10 centimeter inverse, 5 centimeter inverse, etc., can be accepted, but otherwise in principle physically you cannot have the negative frequency for this, right? That
Yes.
uh, right. So but we accept it because computationally it becomes very costly, so everybody accepts it.
Yeah, totally agree, sir.
Well, so and Rahul Bhattacharya has the next question. Rahul, you can
Sir,
unmute and ask the question.
Sir,
yes, sir.
can you
Sir,
give me
for,
one?
Yes, yes. Dr.
Oh,
Sarkar, you have another question?
yes, only one question actually, sir. Sir, in the
Okay.
solar cell calculation, have you calculated this fill factor, and
Yes,
how you
yes.
calculated this I?
Yes. I see. See, in fact, if you see in that table, I don't know whether I have. Yes, yeah. If you see the table, if it is still in the presentation mode, that we have calculated all solar parameter. That means the fill factor also, and here you see that in the second last column or
I
something.
sum E, I and E you have calculated in the first
How?
equation, I and E.
IE, right? Where
Yes,
do you find this one?
J is equal to 0 to infinity, A
Uh,
into, yes,
A is the absorption, right? And I sun is basically you take the 1.5 or 1, that is a value which is I mean that is basically due to the spectra, right? It is given value, so you basically have the absorption here only. Absorption, you calculate
absorption.
absorption spectra,
And the fill
absorption.
factor, how you have calculated? FF?
Field factor, I don't remember exactly now the formula, but we have calculated. And just I will tell you one thing, that you can see there is a reference on this paper, right? So you can go through that, or otherwise you write me, I will give you the formula. I don't remember right now which formula we use, but
Okay,
we
sir.
have
Thank you.
calculated it, right?
Well, so next question is by Rahul Bhattacharya. Rahul?
yes, sir. Yes, sir. I want to know about calculation. If someone calculate magnetic systems, which one is good potential? Which potential is good for magnetic type of calculations? 3D transitions metals like this. Which potential is useful for that?
See, actually, as I said, that it depends on many things, right? But basically, this is by inclusion of U or HSE, right? That is hybrid. Both are quite good in this case.
Yes.
Yeah,
HSC.
so yeah. So next, Rahul,
Yes.
is it
Yes,
okay?
sir.
Okay.
It's
So
okay.
now
So
next thing,
another
you have
thing is that on bulk and surface, suppose in from bulk to surface calculation, how to do this type of calculations means going to from going to surface. See, if you want to calculate the surface, then what type of systems we have required? How we can go from bulk to surface?
Okay. Perhaps I may see what you have to do. You want to know that, okay, suppose you take the two dimension material. That is what is your question?
Yes, yes, yes.
Yes. So, how do you have the idea of using the three-dimensional case
Yes,
calculations?
yes, yes. Bulk I calculate. I know how to
Ah, so
calculate.
so calculate means, or
Means
what do you want to do
designing,
basically?
actually design universal design. I know about how
Oh,
to do it, yeah, in bulk.
you know how to do that unit cell design, or you that also has
Yes,
the
yes,
problem?
yes. I know, I know.
I know. So that means basically that what you take, no. So then, what is your problem basically in this? That is,
So how to do
if you are able to.
calculation on surface, because bulk we consider this is symmetric, and surface as how to means going from bulk to surface. What are the things we required? That is the real things.
No,
Calculation.
you basically take the coordinates, right?
Yes, sir.
So if you have the two-dimensional system, you will have the coordinates according to your system,
Yes,
right?
sir.
And then you take no, that is suppose you are taking the direction. Let us consider, just I'm giving you example 111, right, for
Yes,
the three.
yes, sir. Yes,
So
sir.
in
Yes, sir.
this case, you will take only two. Or then one more thing that you have to give in the third dimension, you have to give the vacuum of maybe 15-20 angstrom.
Oh, okay, okay, sir. Oh, Become in 15 or 20 Armstrong. Okay, sir. I
Yeah.
get it.
Then
Yes.
see, 15-20 is okay, but one should optimize the system with the vacuum also. That is okay. The 15 is okay, 13 is okay, 20, but 15-20 is sufficient. That does not
Okay.
give the interaction.
Okay, sir. Thank you, sir.
Okay, so Dr. Misra has one question.
Uh, s- uh, Jha sir, I have one question regarding that solar parameters. So, do we
Yes, sir.
need to do any post processing for calculating such kind of parameters related to solar application, or it will be just like calculating the energies, or do we have any specific package there in the some software?
Yeah, yes, yes. Man, I will tell you that basically we what we did, right, for our calculation, we did basic calculation by using the density function theory, the DFT code, any of the DFT code, maybe the quantum espresso and the VAST, and then we wrote ourselves various, that means we related to those simple small formula, and we took the parameters from our DFT calculations and calculated those things. So that was the simplest. But there are codes, right, which directly tells or directly gives you all in values, everything related to the solar cell parameters.
But I
But
think not. Yeah, but no, I think not in the VAS for quantum espresso.
no, that no,
Okay,
that
okay.
not in that, not in that.
Then in that case, Professor Jai, I would like to contact you regarding this help actually.
Oh, sure, no problem. Please, please.
Thanks a lot, sir.
Yes, there is a last question, I think, from Rituparna Hajarika.
Hello, sir.
Yes.
Hello, sir. Actually, I want to know that in during band structure calculation, we put calculation equal to bands, and we know that bands calculation is also a non-self-consistent calculation, NSCF, and if we put calculation equal to NSCF, then from there also we can calculate the band structure. So, sir, can you suggest me which will be better for band structure calculation, whether to put bands or non-SCF, because both give the same result, sir?
See, what I could get it from your question. Let's see what happens if suppose you want to have only the bands,
Yeah.
then you do that calculation with
Mm.
the option that is the bands only. But if you want
Yeah.
to use these things to calculate maybe for the density of states and other things, then perhaps you'll have to go for the NCF calculation.
NSCF calculation. Okay, sir.
So therefore, it is advisable to go for all.
Yes, sir. So for band structure calculations, we can go for NSCF. No, means we can get the bands from NSCF calculation. Na? We
Also,
rather
yeah,
doing
yeah.
calculation equal to bands, because when I as we know that when I do bands calculation equal to bands dot calculation for band structure, when I put verbosity equal to high, then I don't get the occupation number. If I get occupation number, it becomes easier to calculate the band gap. But when I do calculation equal to NACF, there I get occupation number, from where I can at least it makes me clear, sir, about the band gap from the data I get. So,
So you do an NCF calculation, right? Because
sir,
that will
yeah, yes, sir. It won't be wrong, na, sir, if I use
no. It is
calculation equal to
no,
NSCF and get the band structure. Okay.
no.
Okay. Thank you, sir.
Thank you.
Well, is there any other question? Yeah, Himanshu Joshi has a question. Himanshu, you can unmute and ask your question.
Hello, thank you, sir. Thank you, Jas, sir, for your beautiful presentation, sir. Actually, I had one question regarding the phonon spectra, sir.
Yes, sir.
Sir, like if we have slight negative frequencies in the phonon spectrum, then is it allowed, sir, for dynamical stability?
See, I will tell you one thing, right, very clearly. The unphysical, sorry, it is unphysical, right? It is not
Yes,
correct,
yes,
right?
sir.
But
Yes, sir.
we accept this in the case because normally in the recent years when the two-dimensional materials have come, this thing has started. That because in the two-dimensional material, it becomes very important to see the stability. So it is unphysical, there is no doubt, right? That cannot
Yes, sir.
happen. But what we say that if you do the calculation, in fact, I forgot to put that slide. I have done maybe some hundreds of calculations just to check with the parameters that what happens or maybe when it basically turns to the real frequency. So if you computationally, if you increase the tolerance, right, or maybe you go for the higher level calculation, at some level, this negative phonon frequencies get removed, right?
Yes, sir.
And therefore, we always say, okay, to save the time, to save the energy, etc. If some little 2-3 centimeter, 4 centimeter inverse is there, that means the system is dynamically stable, right? But in some cases also, you go on increasing the tolerance, it will never be the it will never give you the real frequency. So when you have around up to me it seems up to 5 centimeter inverse, if you have the imaginary phonon, you can consider this as a dynamical stable system.
Oh, sir, so will it be true even for bulk materials, or is it?
According to me, for the bulk, it should not be there because the bulk is already a very stable material,
Oh, okay, sir. Thank you
right?
very much, sir.
And one more thing, that you have to see that where that negative phonon is, right? If it is close to or near the zone center, then it is fine. But
Oh,
if you have at some other point of the brilliant zone, then even if you increase the tolerance, etc., it does not turn to the real frequency. So
okay,
having it close to gamma frequency, 5 centimeter inverse, etc., is okay.
okay, sir. Thank you very much, sir.
Rituparna, do you have another question?
Yeah, so one more question. So
Yes.
when we do phonon calculation, basically, so I'm not as my system has an indirect band gap. So instead of phonon calculation at gamma point, I want to use the K grid. So is it in in the SCF calculation, if I use a small K grid, the same K grid is necessary to use for phonon calculation?
No, no, no. You see
Yeah.
that you when you go for the phonon calculations, and that is
Hmm.
why the phonon calculations are costly. You have to increase the K grid, otherwise you'll get the imaginary phonons or something like that.
Okay.
So,
So that.
so
Huh.
if sometimes no, actually the minimum is that, right,
Huh.
which you get from the electronic calculations. But
Hmm.
when you go for the phonon calculations, several
Hmm.
times you have to increase the E cut,
K
K
grid.
grid, etc. to check the stability.
Okay, so E card also we have to change it.
By changing the E cut, also you can see that sometimes your negative phonons would turn to the real frequency.
Okay, sir. So is there any limit of means how to choose the K? Because randomly, if we do the calculations, that will be not proper. So can we tell me? Huh, sir?
Actually, see, this is all based on your skill, availability, time, patience, and other thing, right? But the
Okay.
basic thing is what, that if suppose you do the calculation for several K grades, or
Hmm.
maybe for the E cut, or maybe for any other parameters, if
Hmm.
you are convinced that you have got the consistency, that means there is no increase, decrease in the values, you can
Hmm.
go up to that point.
Okay, sir. Okay, thank you, sir.
Okay, so thank you, sir. Now, after a very informative and interactive lecture, I invite Professor B.I. Sharma, Head Department of Physics, to propose formal vote of thanks for this lecture.
Thank you, Dr. P.K. Shukla. I thanks Professor Prafula Kesa for the wonderful lecture. Professor Keza has given a very good topic on foundation of density functional theory in two parts, and he had covered most of the foundation of the density functional theory. Professor Keza started a wonderful density functional theory world with the ladder, LDA, LSDA, GGA, meta, hybrid, etc. Coming to the different model, he has covered many approximations such as Thomas Fermi model. He has also introduced how to write down the energy in terms of electron density. This is very important basics of the density function theory, how to write down the energy in terms of density of the electrons. He has covered many important topics. For example, he has covered how to write down the energy as a function of density, then do the optimization technique, variation technique, come to the quantum equations. In the quantum equations, he has introduced the V effective, and the difficulty problem is kinetic energy, function and density. How to handle that kinetic energy as a function of density that he has clearly shown. Coming to the quantum equation solving, he has introduced S-shaped cycles, everything, how to write down the density, electronic density, how to find, how to optimize all these things. After reaching all these things, Professor Kezaha has introduced its application to different models. Even he had covered the variation of pressure. When he covered the variation of the pressure, he has talked about the uh, what do I say, volume, sudden volume collapse. He has introduced B by B, that is called volume collapse. Basically, he has covered almost of the density function theory in a very lucrative way, very understanding format. It's very what to say, very useful package of the density function theory. So I'm very much thankful to Professor Keza for your wonderful lecture, sir. I hope you will be available in the physical seminar conferences organized in our department. It will be very, very useful for the research scholar students and the young researchers, and it will be a very good service to the academician. So I have no any word more than any words. From the bottom of my heart, I am very thankful for your giving time and wonderful lecture, sir. So God bless you, sir. I pray for you, sir. Thank you.
Thank you, Professor Sharma. Thank you very much.
Thank you, sir. So now the second this next speaker has already joined, but let us take a break of 5 minutes and then we will start the lecture at 3:45 or 3:40. Just take a few minutes break. Thank you. So friends, now it's the time for the next lecture. May I request Dr. Misra to share his screen? Dr. Abhishek Misra, the next speaker.
Yes, sir. Thanks. In a while, I'm starting my PPTs.
So welcome friends in the second lecture of the last day of the workshop. And we again have the illuminating scientist Dr. Abhishek Misra. Yesterday we heard about many things by Dr. Abhishek Misra. He discussed about the different applications and the area he himself is working, and then he discussed about the basic aspects of the DFT. Then discuss something about the quantum espresso, and now I hope he will continue from where yesterday he left. So without wasting any time, I invite Dr. Misra to deliver his lecture. Dr. Misra, please.
Yeah, thank you very much, Dr. Shukla. And I will continue from the almost the same uh, point where I left yesterday. Yeah, so we were here actually, and the first step which I mentioned while writing your, I mean, write, writing your input file, or rather, I should say that for doing the calculation is to construct your system on which you are going to work. And for that, you need to write the two things, of course, the atomic coordinates and the lattice. So that's what we learned yesterday. Actually, if you remember these slides, I said there are so many options. Uh, yeah, surface, as the question was asked from Professor Jha as well, that if you are going to work on a surface, you will try to replicate the bulk. But the only difference what we will be having is that I will be having vacuum in particular direction where you wanna study the surface properties, and yeah, like this only. So again, we have some systems where you don't have a periodic arrangement of atoms. It can be a system of, I mean, I can say nanowire or cluster. So in that case, you have to work on supercell. So it time consuming, but there's no other way that you can do such kind of calculations. For example, in the case of vacancy or impurity as well, you have to construct a bigger cell, and otherwise you will see a similar kind of vacancy in just adjacent to the original one, and that's not exactly what you want actually. So in the same case, it is the same case for the system which are not perfectly crystalline. Again, you need to construct a bigger cell. We call it a supercell in our calculation, so that we can mimic the exact same structure. So we are still here where we have just constructed our initial V by giving the input parameters related to structure. And the second thing which I highlighted yesterday is about the why we call these codes as pseudo potential, though we have the other codes as well, like as step and others. Uh, those codes are all electron codes, but usually until unless I'm going to do calculation on some specific system where core electrons are necessary in most of the calculation, it's okay to have a pseudo potential codes where we actually replace all the core electrons interaction, I mean to say potential, by some fixed potential, as I mentioned as a pseudo potential. The quantum espresso is a pseudo potential based code. Yeah, so this we discussed yesterday actually. Because the core electrons are tightly bound, you can valence electrons experience the core as screened by those particular core electrons, and so that we can have an effective potential, the pseudo potential. There are advantages, of course. A smoother potential decrease the number of expansion coefficient for the cone sum orbital, so make your calculations to be quicker. However, there are some kind of calculations where core electrons play a very crucial role in determining the properties. And in that case, if you're using a pseudo potential based codes, then you're not going to get the exact properties of the system. There are so many type of pseudo potentials available, and you have to choose proper according to your system, the property that you're going to expect, as you have learned that how the LDA behaves, how the GGA behaves. So all things depends upon on the system as well as the property that you are going to calculate. As I mentioned yesterday, you can just Google quantum espresso, the potential, and you click on the first link, and you will be ended up here. And all the red ones are the one for them pseudo potentials are available. The files are available. Some people have written it, and you can just click on particular atom, and you will be having so many files associated with that particular atom. So all files are having are the pseudo potential files that you will be using to calculate the different properties of your system. The main ones are your LDA ones and the GGA one. As I mentioned yesterday, that usually PBE signifies that your pseudo potential is the GGA one, while the ones with the PZ usually, yeah, this one is, as you can see here, it's LDA. So then you have the other ones as well, which are uh, is, uh, more accurate. So it it's up to the user. I mean, he has to select the particular pseudo potential based on the literature or the knowledge of the system. So yeah. So suppose I clicked on the oxygen, for example, I will be, and I'm going to use the GGA one. So I will click on particular with the PBE term, and this is the name of, usually it's a name of the scientist, by which they have been saved here in the directory of the directory of the this quantum espresso. It also tells the what kind of exchange correlation functional it is using, and type of pseudo potential. So PBE, exchange correlation signifies for your GGA ones. Say for example, I'm having this BATI-03 kind of system. So the um, format in the quantum espresso is like that. You have to write the uh, atomic mass here and the name of the file here on the third column, and the first column is regarding your particular atom. And this pseudo potential uh, um, is actually going to govern what kind of values you should be using for your cutoff of pseudo potential. So you will open the file and you will get some values, and then again you will have to tune those particular e-cut values so that you can, and you can calculate the exact properties of your system. So some basic kind of errors that you can expect in using different pseudo potential for different atoms. For example, as you can see here, let me use my pointer, that I'm using LDA for the iron, and while I'm using the GGA for the CO. So the problem with quantum espresso is still not very well documented code. I must say that compared to WASP and others. So sometimes you will get the errors which are not exactly reflecting the same thing. The problem the exact problem you are having in your input file, but you need to take care of all these things. Sometimes input syntax is so much, you have to use the exact syntax. If you use extra space or so, it complains. So here is one of the possible error you can have while using the pseudo potential files. So you should have the same exchange correlation function for all the pseudo potential files for your atom in that system. So this is the again repeating the same figure I'm showing you, that I constructed my system. I gave the initial geometry by using atomic positions and the lattice parameters, and then by using pseudo potential exchange correlation, I wrote the Hamiltonian. So uh, yeah, these are the other parameters you will be using your defining your electronic system. So here you have to be very much conscious while starting the calculation. You should use the correct, as much as you can, correct the input geometry. That's what we call it, initial your approximation regarding this. Yeah, the first one, VIN, and then the pseudo potentials and all. So exchange correlation function, again the same. It's how you beautifully write the exchange correlation. So LDA, as I said, that usually it's the files you will be seeing with the PZ name, and while there are others, GGA you'll be seeing with the PW91 and PBE in the name of pseudo potential. So you should not mix all these things. You can calculate separately with the LDA and GGA, and then compare any of your parameters if you're starting the system, and look at how your calculated parameters matches with the experimental one, and then you can decide whether I'm going to use the LDA or GGA, or even some advanced one like the U parameter or the hybrid function also. So diagonalization of the matrices are of course expensive, and but uh, so you have in your quantum espresso different of diagonalization methods, and you have to choose the one which give the correct results actually. And then so what we started from this point, by giving the geometry of our system, we selected some pseudo potential files, approximation, exchange correlation function. Depending upon them, we selected some cut values, and then we calculated the new density. And now the SCF thing, we have to compare whether they are close. And of course, one of the most important thing that as we are going to work on a material, not molecules, so we have to give the K points, and there are some different methods by which you can use the William-Jones sampling. So usually in the most of the cases, we use the automatic option in the quantum espresso, while there are some other options as well which are available, and you can compare them. So of course, we usually work on a distributable Boolean zone that can replicate all the my complete Boolean zone. And yeah, usually the problem arises with the metals, because metals have sharp discontinuity, and that's why you have sometimes the electrons sitting on the valence band area as well. So we need to have be very cautious while we are working with the uh, metals. So because in metals usually we have a band crossing. So this problem is solved by smearing. Actually, it is a mathematical trick. Nothing is having significance in the experiments. So may I request everyone to switch off their mics? So usually what we do, the problem is in the metals is that when you have the sudden discontinuity when we go from the valence band to the conduction band, and for that we use some extra functions here, and it's how we control the filling of electrons in the bands actually. And this helps us to control the error which can happen in the case of metallic systems where we have a bands crossing. So there are different methods. You can go to the these PRBs and PRL papers, and can understand how different methods in the codes are differing and which type of sparing you should use. And then again, I'm going to check whether now our calculations are self-consistent or not. If it is, I don't have any problem. But if it's not, what we should do? So we should again go back to the initial point where we have to write our densities. So what we will do, we will calculate the density of our nth and one step before that, and if they are really close enough, and then I'll say that consistency has been achieved, and depending upon how much conversion threshold you have given in your input file, so the code will say that okay, now SCF cycle have been done, and then I can calculate my forces, then I can calculate the other parameters. But usually it goes through the many SCF cycles, and because your initial geometry is most of the times is not very close to what it should be. So in that case, what I will do, I will take some part of the output geometry and mix with the initial ones, and then again do the similar kind of step as you can see here, calculating the Hamiltonian and checking whether it's self-consistent or not. So there, what I explained, that I will mix the output to the input, and this is known as mixing. So I will be having my old density, which I had in the starting, and what I have now after the one SCF cycle. And what I will do, I will take some part of the output and will try to write my fresh density by using that output density. So that will help me to converge my system quickly, and that is being used in quantum espresso by using the input parameter mixing mode. And usually uh, so it's between I mean, you should use zero point 0.1 to zero point 0.9, but usually what we do, if you're using a zero point 0.9, it's not going to affect a lot your input geometry. In that case, you will be ended up with the again wrong densities, and your calculation will not be conversed. So usually if you have more and more time, and uh, you have uh, your system is very small, you can use values like close to 0.1, 0.2, 0.3. But if your system is really very big, you cannot afford to have a month's calculation. In that case, 0.5, 0.7 also works fine. Do is based bigger your system is and how much computational power you are having and how much time you're having for the calculations. So this was so far related to the input parameters that we use in quantum espresso while we start doing the calculation. So far the SCF cycle I have shown was telling you that how you are going to relax the electrons in your system. But when you have a molecule, when you are having a system, I say the material, you will be having so much of ions, and for every ion you will be having electrons, I mean electrons. So far what we have discussed was related to the electronic SCF cycles, where we are trying to get the electronic density accurately. The same principle applies for your ions as well. So once I'm converse the my electronic SCF cycle, what I will do, I will calculate the forces, and if my forces are close to the tolerance level that I specified or close to zero, then it's fine. But if not, and usually it's not actually, because your initial geometries are, as I mentioned, are not very close to what it should be, then in that case you have to move your ions, you have to displace them by very small amount, and then again repeat the same thing. So there are always two type of SCF cycle you will see in the output of your quantum espresso. The first ones, then is uh, ones are your SCFs related to electronic motion, and then your ionic motions. So in each ionic motion, you will be having so many electronic SCF cycles, and then so many ionic kind of SCF cycles will be there in your optimized results that I'll be showing you in a while. So for doing the, I mean, usually that's what we must do, is to relax our system. And so every calculation starts with this: calculation is equal to relax. So by this tag, I'm telling my code that you have to do the structural optimization by using this tag. So there are some choices as well, that how you are going to, which kind of algorithm you are going to use. I'm not going to detail, but you can choose depending upon how fast or how accurate you want your results to be. So there are two things actually. Usually we write can relax. So when we are going to write the relax, your code will only optimize the atomic position in your file, and it won't relax the lattice parameters. And as you can see here, let me just go back again. It's always a good way to explain. So what I will do, I will write quantum espresso input output description in Google, and I will be clicking the first link, and I will be ended up here. So if I click on the calculation, you can see here there are so many options, and uh, usually we start from here, relax. But relax is not the most accurate thing that we should do to our system. It's always preferable to relax, complete your structure. I mean to say the atomic position as well as your cell parameter. So in that case, we use VC relax, where VC means variable cell relax. However, sometimes when we run VC relax, y- depending upon the complexity of your system, it's not like that when you put the VC relax, you're going to get the similar kind of structure that you gave in the input file. Sometimes geometry breaks because of the symmetry constant and all. So in that case, you have, when you're using the VC relax type, you have to be very cautious. You have to look into detail of the output, whether my input and output structures are somehow close to what we are expecting, or my output structure is really different from what it should be. So it's not that easy to use VC relax, I must say here. So I'm again back to my PPT here. So for documentation, as I have already shown you that you can go to the input underscore pw.html and look at the different contents. So namely, this is one of the main tags actually, the control system and electrons. As I mentioned that in the control you will specify that what kind of sorry, yeah, what kind of calculations you are expecting, and under this ampersand system section in your input file, you will specify your system, that how many atoms are there, how many varieties of atoms are there, kind of things. And then under ampersand electron section, I will mention what should be the cutoff for the the electronic convergence criteria. Uh, these are details you will mention in the electron subsection. So these are sometimes optional as well. So the code will take the automatically what is default one, but as you will move in this type of calculation, and you will understand better actually. And then I have to specify my atomic species, that what are they. Suppose you remember BATI, BATIO3, so I will specify BATI, and then you have to write the K points. So K points, I think you all understand that they are related to your lattice parameters. So if you're having A, B, C as the three lattice vectors, so my K points will be having a reciprocal kind of a relationship, because you are defined, and you know it is 2 pi by A, 2 pi by B, and 2 pi by C. So what K values you have to choose depend upon your system geometry. If I'm having ABC values same, I will use the K1, K2, K3 as to be same. If not, I will select those K1, K2, K3 as per the values of ABC. If A is the largest, my K1 will be the smallest. So you remember the formula, k is equal to 2 pi by lambda kind of things. So it's just the opposite. So there's other features as well. You can do the magnetic calculations. You can calculate the phonons by using the perturbation theory. I saw you yesterday, and Professor Joe also mentioned regarding the MEB calculation, which are really, good in terms of many applications in the catalytic calculations specifically. Then we can do the MD and so many things. And yeah, it's a plane wave calculations where we are using a pseudo potential actually. So most of the slides I use from the Quantum Espresso website from a school and mostly from the Professor Sobna Nashima from the JNCSR. And before I jump to the technical content, I would like to acknowledge my Professor Umesh Wagmare from the JNCSR, from my guide there, and for all the training and knowledge. So yeah, let me jump to the terminals and show you quickly few basic calculations. Good. So what I have done, as I mentioned yesterday, that what you should have done so far is to type quantum espresso tutorial on the Google and click on the first link and come here. So as you can see there, this a particular page list different kind of workshops in the past, and um, regarding sometimes PPTs are also uploaded, and ones I like regarding the basics is on this one, hands-on tutorial of quantum espresso. I must recommend everyone who is in the learning stage to go through it. And once I click on this, I will be here, and it lists all the things that you can do related to installation of quantum espresso. I'm not going to uh, explain the installation at the moment, but it's a really good slides. Then what you can do, you can click on the write up and exercises, and you'll be having the PDFs with you. So the PDFs I have opened it here. I will try to explain the few things from this PDF, and you can download that PDF from the web page of the Quantum Espresso tutorial. So the first thing that we learned so far is doing the, I mean, in the DFT, what we have to do, it's based on the self-consistent approach. So we'll be doing the SCF calculation for the silicon first, and varying the different parameters what you should do while doing such kind of calculations. So it says that you have to download this hands-on underscore pw dot scf dot tgz, and then of course you can untar the system by using this command. And once you have unzipped the file, you will be somewhere here, hands-on pw.pwscf, and these are the contents you will be seeing. So this is the PDF which I was referring, and it consists of so many different kind of folders based on different kind of calculations or the different kind of systems. For example, in the iron folder, iron is a magnetic system, so iron is also being listed there, and that folder will tell you about the magnetic calculation. Let's start using the silicon one. So I will go to my PDF. So it says that move to the silicon subdirectory and look at the input file si.scf.in. It consists of three, namely control and so, and you have to write the appropriate variables actually. So that's what we are going to do to give a scratch training, because these are ab initio codes, and it's the name suggests it's ab initio. So I'm starting from the scratch. Yeah. So is that you have to go to the si.scf.in. So if you uh, look at this file, I haven't edited this file. This is the file you will get when you download that zip folder. So again, as I mentioned in my PDF, that the first section is control. Every section starts with the ampersand, and then you have a control, you have a system here, you have a electrons here, atomic positions, atomic kind of things. So the first one is also important, where you have to write the prefix. Prefix means you can write anything here, A, B, C, D, your name, whatever. But you it's preferred to write the system name. And what it does, as you can see, you have a line here, out directory. Out directory is a directory where your output files will be written. So usually we don't need all the file that have been written there, but sometimes while doing the like DOS calculations, while doing the bands calculations, those files are required, and the code itself read those files from the output directory. So you have to specify the path of the output directory where you're going to write them. And then the thing is a sudo directory, where you are going to specify that where your sudo file is located. So it's your job to go to the sudo potential web page, download and save in a particular directory, and give the path here that wherever you are saving that sudo potential file. And then the second is your system. So let me go to the input. Yeah. So as I said that you had to write the two things here. One is the output directory, where the code will write the temporary files. And the second is the sudo directory. Sudo directory is the one where you're going to download, save your sudo potential file by downloading it from the website. So usually what we do, we go to the just a second. Yeah, usually what I will do for the pseudo potential things, I will go to the home. Yeah, pseudo potential, and suppose I'm going to work on silicon. So this thing I have already done. I'm just showing you quickly that for the person who is just starting these calculations. I'll click on silicon. And then if I need the GGA one, I will look for the PBE ones. And if I'm looking for the LDA ones, I will use the PZ ones. So suppose you want to use this one, so I will click on this, and I will save it as a text document. Yeah, second thing. So again, I will show you how I have written these two things in my file. Now let me show you actually. So I have created one more folder here actually with silicon test name, and my File is like this. So I said that, okay, prefix is silicon, as I kept it the one it was written. And sudo directory, I said that it is my sudo file is in the same folder. So this signifies your present working directory. And then I have given a folder name tmp. So that tmp folder will be the folder where my code will write the temporary files while doing the calculations. So let me show you. So this is my downloaded pseudo potential file. So this way you have to go to the website and you have to download it in a folder and give the exact path in your input file. And the second thing which you have to as I must explain, is how you are going to define your structure. So it says that in the red color, I brave is equal to 2, meaning FCC lattice. So in the quantum espresso, you have an option actually. If I click on I brave, it's how you're going to define your Braves lattice, how you're going to define your structure actually. So there's depending upon your structure, it has some specific tags that you can use. If you have a cubic ones, you can write I brave is equal to 1. If it is FCC, I can use I brave is equal to 2, and so on. And if you don't, if you have a 2D kind of system, or a system in which you wanna specify your system by yourself, in that case, you will use I brave is equal to 0 actually. So it's a free, and you have to specify the cell parameters. Cell parameters in the form of your tensor vectors actually. So AXX, AXY, AXZ, then BXX, BXY, BXZ kind of things. So if you look at the PDF, it says that they have selected 2 because it was having a FCC lattice. And second thing, I would like to mention here that everything is in the Bohr unit in the your quantum space of calculations. And I said that in under system, you have to specify a few things: how the structure looks like, how many atoms are there. So in my lattice, I have 2 atoms here. As you can see, this one, the corner one, and this one, and this can beautifully replicate my complete structure. So that's why they have selected n at is equal to 2, n type is equal to 1, because only one species is there, silicon. And yeah, that's it regarding the structure. Let me again go back to the system. So I define my control section here. I define my system. So these things, E cut WFC is basically defined by the what kind of pseudo potential you're having. So you will define your cutoff values for your plane waves energies. And then I have to define my atomic species, my positions. There are so many units, angstrom, allot, elat, and the crystal, in which you can define your atomic positions. And then the last one is defining your K points actually. So K points also can be defined in many units. Usually everyone prefers until unless is specifically required, we give in the form of K points automatic. So this is the folder I have prepared, the test folder where I have tried to edit the file for the better. So I defined my sudo directory that it is in the sudo folder. As you have seen, I have defined a temp directory here. I have created I have chosen this ecut wfc to be uh, 38 y38. If you look at the sudo potential file, if I open this file, you will see here actually. Yeah, so it is somewhere it's written as yeah, 38 with birth should be the your standard, but it's not like that you can blindly accept these values. It just gives you a starting, or I will say it's just a close guess of what you should start. So that's what I have I have written there in my file. If you look at again this SCF file, and then silicon is silicon, no issues, atomic mass is same, and then uh, LDA kind of pseudo potential that I downloaded, I have written it here as you can see, si.pz, this one. Yeah, and yeah, atomic position I haven't changed, but you can change it as well. And K points, it's because your lattice parameters are the same ABC values, so I have used 2 2 2. I mean the K1, K2, K3s are same because ABC are same, and 111 is the format actually. So before I start, it's always better to look at how your system is going to look. So I will use X Kristen for the same. So it's a FCC type of structure. So here, the beauty of X Kristen is that you can have a look at the details of your structure and can verify before submitting your job whether this is the one that you're expecting or not. You can note down the atomic distances by clicking on any two um, atoms and can verify yourself whether it's close to what it should be or not. So other things are there. You can play with the X Kristen and can note down many things. Specifically, it helps while we do the calculation regarding the band structure uh, to have the K point grids, and it also helps when you try to do post processing and calculating the electron density maps. So yeah, we'll come to this part if the time allows. So, so far what we have done, we have tried to write a very simple file for silicon. We have written where my pseudo directory, where my output directory, what my ecut WFC value is, what pseudo potential I'm going to use, what are the coordinates, and what are the key points. So once I am happy, I try to visualize that system, and it was looking good, so I can run the calculations. So I have already the results with me, but what you can do, you can always locate your pw.x executable and can go to the bin one, the one with the bin, right? And then your input file. There can be so many input files, but we are going to use this one and output with some different name because one is already there in my folder, so it won't overwrite actually. So the problem was that I typed here CD actually. So it says it's done. And if you see that, yeah, I have this new input output file here. It started just now, and because we have only two atoms, very simple system, so I'm able to complete it in just a few seconds. And if I go at the end of the file, it will uh, it will say that BFGS converged. BFGS geometry converged means even ionic SCF cycle have been done. These are the optimized geometry that you can take from the file, and you can see that the forces on atoms are zero here. I mean, sometimes most of the times it's not zero actually, but they are close to zero. Even then, we see that okay, let's go ahead with the calculations. So this is how your output file looks like. So because our system was so simple, only two atoms, and that were two already fixed at the same point where it should be. So that's why you can see that our ionic ions were at the perfect position. That's why it took. I mean, yeah. The second thing is that the reason we haven't done the relaxed calculation, we have done only the SCF calculation. If you look at the input file here, so just note down this calculation. Okay, so it might be the reason that because it's already optimized geometry, so that's why it's our output is like that. I mean, it was so quick. Then now that was just a trial kind of what you should do at the starting. But the problem is that if you look at this file, there are always a few things that you need to optimize. One is that this equal WFC value, and the second is your K points. So what we should do, we should vary it from about 20 to 40, 50, 60, and try to calculate the energy of your system by using the different values. And for the one we are getting the minimized energy, we should use that E cut WFC value. And suppose I got the minimum energy at about 40. So I will fix the 40, and then the next step I will try to modify these values, the K1, K2, and K3 values. So I will start from uh, the smaller numbers 222, then I will use 333, 444, 555, and so on, whatever I mean how much you can afford. And then I will do the same thing. I will again plot the variation of calculated energy with the K points. So if you look at this yeah, if you look at this output at the end, it prints, always prints energy. So this is your final energy. Yeah, we in the quantum espresso we don't have any. I mean, or in all the DFT calculated energy, actually they are having no significance. The absolute energy values are having no significance, but it's the difference of the energy which we note down. So what I mean to explain here, that if you are using PBE, you are using some different functionals. It's very much obvious that suppose I'm getting minus 89.27 from LDA, but suppose I'm going to use PBE, the GGA ones, I will be getting any value, random value, minus 260, minus 150, or whatever. So that's fine. There's nothing to worry about that. Uh, what I should do is to change the our basic parameters like E cut WFC value and K points and note down the variation by keeping the functional same. If you look at again, let's go there. It's again explain the same thing that you should use the key points and blah blah and what the it again explains that how you should run. That's what we did actually, and it says that you can have different values of energies and the final energies at the end of your file, and which is the lowest energy. If you look at these values, you will see that this one is the printed at the end and is the lowest value. So once it's being done, you can move to the next step. Now, as I explained, we have to check for the convergence of our system, electronic convergence we are talking about at the moment, electronic convergence, by varying these values. So uh, we selected about 38 or so, but yeah, we can vary this, and can we ideally we should run pw.x for each and every value, and then plot the output energy against these values. So that's what is being explained here. Actually, you have to plot the total E total versus E cut, and you will get such kind of graph. So let me see if I have done the similar kind of stuff and I can show you. So I don't know. Yeah, I have prepared E cut folder here, and I have varied, as you can see, there's different folders: 10, 20, 30, 40, 45, 50, 55, 60, 70, and if you look at any folders, let me go to the initial one, C10. I mean that 10 folder, and if you look at the content of my file, look at this. E cut WFC is equal to 10. This is the only difference. Otherwise, the complete file is as it is. And yeah, and similar kind of things you will see in the this folder. If and the E cut WFC is 20 here. So what I did here is I varied the energy values, and just look at the files here, output files. So what I will do, I will type them as in the command grep. Yeah, I will go to particular folder, and so this is my final energy. So why I said that, and why I type this grep is to grep, and this exclamation marks actually when the quantum espresso prints the energies, it prints a exclamation marks there. So what I did, I tried to grab this, and it automatically gave me enough energy. So in this way, you can write down your energy values, and you can prepare a file like this. In the X, I mean, in the first column, I have a different WFC values, and in the second column, I have my different energies, calculated energies, and then I will use this command. I mean, this software XM Grace, which is always available on your Linux terminal, and I'll try to plot that. And you will see graph similar to in the PTF, that if you remember when we opened the pseudopotential file of this silicon, and the prescribed value was 38. So the similar what we got here actually, as you can see that the energy was very high here, and then it decreased at 10, it was very high, 20 decreased, 30 even decreased, 35 also a bit decreased, here you can see, and then about for close to 40 we are getting almost the same energy. So the point where we are getting no variation in our output to DFT calculated energy, that point we can choose. I mean, of course, you can take 50, you can take 55 or so, but it will take more and more time, and hence we will take just a starting point. So yeah, so our result so far was that I should use 38 or 40, close to that. So that's what I did, and the second step will be, as I mentioned, or as this guy will mention in the PDF. The second, as yeah, here as well. So, I mean, because we have used the difference of the potential, that's why our results are different. Actually. So second is the convergence of k points. So again, the same procedure we will follow. We will so far we know that you have e cut value, which is it should be about plus in the star from the lower value, and I will keep increasing. So that's how one should do. And then yeah, the same thing. We can vary the key points here, and you can plot using GNU plot or XMBase. XMBase I like for the simplicity, but GNU plot is also a powerful plot. So this guy is saying that 2 is having very high k values, and you will see at 3 decreased, 4 decreased, and about 5 again decreasing. So you can choose somewhere here actually. No. So far what we have done is we have calculated, I mean, we have done the SCF calculation. SCF calculations means the electronic SCF calculations actually. We have just determined the values of your plane wave cutoff, so energies and K points. So 20 and 441 were the optimal values. That's what we got. Now, the second step is to determine the accurate lattice parameter actually. So, how we shall do that? They have, I mean, we have created a script for that. What this script will do, let me show you. That it will vary your lattice parameter from some point to some point, and we will plot the energies here like this graph, and at the lowest energy we will select the standard value for our further calculation of your this lattice parameters. So let me go back to the terminal. Yeah, so I prepared this equation state. If I open this script file, so the one I did for the case of E cut values and K point was the manual type of doing that, but you can also create a script file like this. You can use any of these scripts available there, and can play with this depending upon what you're going to do. So what this guy, what this script does is, of course, you have to specify your output directory. So I specified it like a present working directory by dot and slash, and I said that okay, yes, my pseudo directory are also in the same folder where I'm doing the calculations. And now look at this. Uh, I said that my cell dimension are not fixed. I have given some variable name here by using this dollar and some value here, and I have specified that you have to work as a loop doing multiple calculations by varying the elite values from 9.8 to 10.7. So what I did, I had some initial idea that it should be close to 10 or so. So I went to some I mean, negative direction and some positive direction and tried to calculate the energies. And I will see that what is the effect and what is the optimum value of lattice constant I should be having for the silicon. So that's it, I think. So that the code will do the calculations. So it's an end of file here. And this is the path where my quantum espresso code is. So, and then it will grep is used to grep the things. It will get the lattice parameter and the using the ampersand symbol and the file output file name si.eos.out. I will grep my energies, and I will write those in si.e versus a lat. So different kind of file for the plotting. And you can notice here that we have used our optimized values of k points here and optimized values of e cut wxc. So I already ran this calculations, and now I have this. So if you remember again, let me help you with this code. If you remember, let's see this file. It says that remove si.eos.out. So what it will do, it will and what it will do, it will remove these calculations after going through this loop. But at the end, for this value, actually this 10.7 values, it will start from the 9.8, and it will calculate the energy. It will again come back here, it will delete that file, and till 10.7 I have asked to do this. So this will do it. So till what? 10.7. So if you look at this input file, I believe, yeah, if you look at this file, I haven't prepared this file manually, but because of the way we have written that script file, that end file was not deleted. Now I have this file e dot versus the lat. Look at this file. So you can do it manually as well. You can do it by simple script file and running that by using sh command. So if I plot this by using the same xm grays, I will have a similar kind of stuff. Look at this, 10.2, close to 10.2. I'm having the minimized values. So I will select this. So that's done regarding how you will play with the values of cut, how you will play with the values of key points. I mean, how you will optimize actually, and how you are going to find the lattice parameters if you have simple case of where you have ABC same values. So yeah. Now the next step is to calculate the bands actually. The bands is rather what I can do is going to DOS first. No. Yeah. So yeah, the reason I did bands first was, yeah, this is the same graph we have seen in our terminal. And I'm happy that I have found this value as the optimized meta parameter. So as you can see here, this guy have mentioned again to show that how beautifully it is LDA and VJ captures sometimes the these lattice parameters and related things. So LDA is giving you exactly same lattice parameter of silicon, which is close to 10.26 angstrom unit. So now next task is to look at the bands, and for doing the band calculations you have to do first structural calculations, and then SCF calculation, and then NSCF calculations, which is being done by using the script bands. So if you look at this, I have my input file, first input file actually, where I have my coordinates, atomic coordinates, which I know that they're good, and I know that this is the lattice optimized lattice parameter, optimized value of lattice parameter. So I'm happy with everything, and hence I need not to further relax it. But usually we do the relaxation in kind of real systems and or even VC relax, because not every system is having the same ABC parameters kind of things. So, but here for the sake of simplicity, we have done in that way. And then if I have not written what kind of calculation it should do, it will take the default values, and the default option is SCF ones. If you don't believe me, you can go to the website and click on the calculation, and it will default value is the SCF one. So that is why I did not mention it, because it will take automatically the SCF tag. So this is the first step. You have to do SCF calculations, and my output is here, si.eos.out. It's almost the same thing what we did in the first calculation, but here the more accurate values regarding. So once I'm done with this, my next task will be to do the NSCF calculation. But yeah, so the format of NSCF or bands actually is same as what we did in the case of SCF ones. The only difference will be so let me open the bind file. Good. So let me proceed with the first point. So everything is same. The only thing that you can notice is that I have written specifically that we have to do the bands calculations, and yeah. So this is the difference. Otherwise, this is same. We cut the value that we have already determined. This is the same assignment position, same. Now key point we have to specify, and we have to specify in the in a form of a grid actually. But the question is how we are going to get these grids. So this depends upon the symmetry of the structure. What I usually do, and what many people do, is to use the XPresden to generate that. I will open the file in the XPresden. My structural file, you can take any SCF file or the relaxed calculations. It's the same file actually. If I put S, I will see that silicon, yes. So nobody can say that I'm using a different file. I will go to tools, and I will go to the K point selection and say okay, close. It will open your primitive building zone actually. And here you have to choose the minimized irreducible building zone actually, that part which can reproduce your complete building zone. So I can take any starting point like this, comma point, and likewise you have to select the other K points, which if I select it should produce my complete building zone actually. So if you're taking more points, there's no problem at all, but you should not be missing any important K points. It's just randomly I'm giving the example actually. So once I'm done with this, I will say okay. And it asks that how many K points. So what we do, we select the high symmetry K points here, and then you can break those K points into you can further break those points along the building zone, and more points you are taking, the more accurate calculation you will be getting. Otherwise, it will just plot a graph with connecting too far K points. So let's say I say that I have to take 36. and then I will select some new. I have already done actually. Okay, points 2, and I will save it. That's it, and it these different kind of different K points breakup as per those high selected K point grades. So now I will close this. I will go to that file and I will copy as it is this from here to the end, and I will paste it in my bands file or NSCF file, whatever you want to say. So if you look at, if I open it again, that's what I have done it. So I have my good structure. I have SCF calculations in the same folder. I am going to run the bands calculation. So I will try to find out where are my bands executable, and yeah, I will do this. Then log in, because I already have one. I will use some new name. Some errors, I don't know. Sometimes it's really difficult to find out the error actually. So at the moment might be some typo errors are there, but when I did the calculation, I found this output file here, which prints all the K points, eigenvalues actually. And once I successfully run these calculations, the next step is to do post processing, and that is available by this format actually. You can see in the PDF as well. So the only thing that you can change here is the LCM is equal to true, because sometimes your symmetry matters, but only this will, if I'm saying that it should consider a symmetry, your calculation should be quick. Otherwise, it will take it will do the calculation on the complete join. So the second next file is to do such kind of things where it will give you the details regarding the K point energies. Oh yeah. So the reason why I was getting, so there are two things. If you remember, we did the first the SCF calculations by using this file, and we got this. And while using this, I mean that was a mistake I did. Then I created this file, which I said that this is the NSCF file. The only difference here is I have used the bands and I have used the K point grid here. So while using this, while running this file, we should use the pw.x executable, not any other. So if I use this, I use the pw.x executable, which is here. Sorry, yeah, and my file name was, I don't know, band.in and band new dot out. So it's running. I'm done. So I didn't got I did not get any error here, and this file is same as what I already had actually. So once I'm done, next task is to use these calculated values in a plottable form, and for that the format is like this, where you have to use the same prefix that we are using prefix, and you should be using the this name, I mean the name that we got uh, for the band, and I will be using the executable bands.x here. And it's done. Yeah, I'm done. So you can see that these are the two files have been generated by the code. One is the silicon.dat band2. So we just need these two files to plot further our band structure. So uh, we have one more utility in the quantum espresso actually, which is known as plot band.x. I don't know whether it's being mentioned in this PDF or not, but just a second, guys. Yeah, you can use directly. Yeah, they have used plotband.x. So you can just type plotband.x and give this file, or can create a very easy script. That's what I created here, plotband.in. So what I'm saying here, the first line signifies that from where you have to use the band energies, and what are your in the energy range. So I said that maximum minus 15 to 15. Then I have said that it should create a some grace file. Uh, so this is the name that I have given. You can choose any name here, but this should be the same as what we got after running the bands calculation. And if you want to create the PS file, you have to give the Fermi energy, but I don't care about the PS. I just need my XM grace file. So I have just kept it like that only. So let me locate plotband.x. Yes, we have it, and uh, I will click on this plotband.in and plotband out 2. Why 2? Because I already have one, so I don't want to override it. I don't know. No, so it's one. So we have this XMGray file here, just created now. So you have to believe me that I am not doing any magic. And we have the energies for different key points, and you can just use XMGrace and this silicon.xmgr, and you'll be having some plots like this. So as you can see, you have a these are the high symmetry points, and we need to just draw the vertical lines so that it reflects the same as we see in the our papers. We can play around with the K points also. So this is how we plot the band structure actually, and yeah, I think I'm done. I won't be able to show you much details regarding the phonons or the further calculations. But bands in DOS is the same actually. In DOS, what you have to do, you have to do the relaxation of your structure. You have to do the SCF calculations, and just from the SCF calculation itself, you can use the DOS DOS.x executable file to run. But what we do in the real DOS calculation, we use an NSCF calculation, and NSCF calculation is nothing. It's just same calculations on already calculated grid by giving more number of K points. So that's it regarding my side. Over to Dr. Shukla. Am I audible? Everything is connected?
Yes, yes, you are audible. Dr. Sarkar, now you can take a couple of questions. Dr. Sarkar?
Yes, sir.
Yeah.
So, uh, Professor Misra has finished, I hope.
Yes, sir. Yeah, I'm done.
Yes. So, thank you, sir, for giving this nice presentation and this hands-on. I hope all the participants are very much gainful for learning these SCF calculations and convergence criteria to the fund structure. And now the session is open for question, and up to 5:15 we will take the questions, and then afterwards whatever the questions are left, you can directly call with the Professor Misra, or if Professor Misra is available after the valedictory sessions, then we can continue. Okay. So the first question is Priyanka. Priyanka, are you here?
Yes, sir. Good
Priyanka from
evening, sir.
IITBHU. Yes, please.
Yes, sir. This is Priyanka from IITBHU. Firstly, thank you so much, sir, for such an informative session. Actually, sir, I have some doubts. When I calculate SCF, then during SCF, after SCF calculation, we go to optimization step. And during optimization, firstly, like I optimize my K point and I increase the K mass. And after increasing some points like 2, 4, 6, when I reach up to 8, and I'm facing the error like Sidiag error, that is Cholesky error. And when I search about it, then I got this is due to uh, closeness of closeness of atoms, and this is unphysical structure. So, how can
Yeah, so this kind of things happens many times, and we are not able to exactly dig out what the exactly problem is. So sometimes it's the method by which we are diagnosing the matrix that causes the error. And if you believe that your system is really, simple system, and you're not having any kind of molecules over that or some complexity,
yes, sir, I
and
have
then
a
yeah,
system. I have system like MOSE2, then there are two types of atoms. Then I am facing this problem. Firstly, sir, I'm not able to finally select out how much ECAT WFC I have to stake in starting. Because when I start from the like minimum value 20, then I found that there is no cutoff, there is no available plane waves for the calculations. Then I increase this value and optimize it, and again then I optimize K points, then I'm facing that issue.
so what I can suggest here, what I can suggest to you is you look at the pseudopotential files and look at the suggested values of ECAT there. And suppose you are having 8 atoms, 8 kind of atoms, then
Yes, sir.
what is the maximum ECAT is suggested? You can start with that actually, and just play around with the small. Suppose if it's selected like a 40 or 45, I think from 25 to 35 you will see 25 to 40 you will see in all the pseudopotential mainly. So whatever is the maximum value of your particular so see if it's MOS2 or so molybdenum and the sulfur, and try to start with that value, and just a small increment should do the job. I believe if it's still not the case, that I will have to look at your input file actually, but usually it works. And K
Okay, sir.
point again, those kind of errors are sometimes get solved by either your structure is very complicated, or by changing the method of diagnosation and all.
Okay, sir. Sir, I have one more question. Is it any problem
Priyanka,
in... Yes, sir.
if you can, I should give a chance to other people also. So it's better if you can wait until the valedictory is over. Then if Professor Misra is available, we will continue. Okay. So the next question is Devasi Pal asking how to decide if we could use a unit cell, a supercell, or slab model for calculation. How to decide?
Y- Yeah. So until unless I'm going to do any kind of calculation which really require the supercell. For example, suppose I have a 50 atom cell, and I said that you have to have 10% or 20% doping. So in that case, I need to increase my cell size. If I am not going to do that, my your doping concentration will be higher, because your image of the dopant or the image of the defect will be just next to the original one, and you are not going to get the accurate result. So such kind of applications where we are going to have a look at the defects, dopants, or even the interaction of molecules. So if you have a very small cell and you are going to look at the examples like CO2 or any molecule interaction for the gas sensors or so. So in that case, usually we try, I mean, it's better to avoid the effect of periodic PBC conditions implemented in the code. So it should be having at least about 8 angstrom or so between the distance between the two molecules. Otherwise, those effects will come into the picture and you will get some different result. So this is how we decide where we are going to work on a smaller cell or the bigger cell.
Abhishek, sir, may I request you to kindly answer the questions after the valedictory sessions. Please be
Yes,
present with us.
yes,
So,
Dr. Sukash.
so all the participants, please bear with us. We are running short by time. It's already 5:15, and our guests are waiting. So we will continue this session after the valedictory is over. Okay. So hand over to Professor Suklaji.
Yeah, thank you, Dr. Sarkar. Uh, I welcome you all in this validity session. This is the time for validity session, and now I invite Gulab Shah to take over this proceeding. Dr. Gulab Shah, she is our research scholar from the department. Gulab Shah, you start.
Yes, sir, sure. A very good evening to respected head of the Department of Physics, Professor B. Indrajit Sharma, respected coordinator of the workshop, Dr. P.K. Shukla, respected chief guest, Professor K.D. Shen, University of Hyderabad, our guest of honors, Professor Prafullo Kumar Jha, the Maharaja Sayajirao University of Baroda, and Professor Abhijit K. Das, IICS, Kolkata, Dr. Abhishek K. Mishra, Associate Professor, UPS Dehradun, Professor S.N. Thakur, BHU, Varanasi, respected faculties and attendees of the conference. I, Gulaksha Chaudhuri, Research Scholar, Department of Physics, on behalf of the organizing committee, welcome you all to the valedictory session of virtual workshop on density functional theory and its application. We have successfully come to the end of 5 days long workshop on DFT and its application. Renowned physicists blessed us with a series of some great lectures, which I am sure of great benefits to the participants. Uh, with this, sir, do we have Dean sir with us?
Yeah.
Okay, sorry, sir. I did not see his name actually, so I did not introduce. I would like to welcome our respected Dean, School of Physical Sciences, Professor Chidaranjan Bhattacharjee too, in this valedictory session. Okay, with this, I would like to request Professor B. Indrajit Sharma, Head of the Department of Physics, to give the opening remarks. Sir, please.
Thank you, Gulab sir. This moment is approaching to end of the 5 days virtual workshop on density functional theory and its application. It is quite difficult for us, the time reached, to separate among ourselves, especially resource persons and participants, after a close interaction of 5 days teaching learning sessions. We, the academicians, are happy to join interaction in seminars, workshops, conferences. I hope the participants have learned a lot during this 5 days workshop, having 10 dedicated lectures by the eminent resource persons specialized in DFT and its applications. Taking this opportunity, I thank especially workshop coordinator Dr. P.K. Shukla for playing a key role for organizing this program, and my colleague faculty members, research scholars, for giving full cooperation to make this program a grand success. On behalf of the department, I thank Honorable BC, Dean School of Physical Sciences, Professor Sher Bhattacharjee, all the resource persons, participants for support making realization this workshop. We hope in future we will meet soon again in offline workshop in the campus, and we invite all to visit department in Assam University campus. Thank you all. Thank you. Over to Gulab sir.
Thank you so much, sir. Now I invite our guest of honor, Professor Prafulla Kumar Jha, the Maharaja Sayajirao University of Baroda, to speak a few words. Sir, please.
Sir, you are muted. Sir, you are muted.
Okay, thank you. So good afternoon from our side and good evening in your side, because there must be some evening now. Chief guest Professor Kalidas Sen, sir, Dean Professor Prantik Bhattacharjee ji, Professor Sharma, head of the department, Professor Dr. Shukla, who has organized the conference or the workshop, Professor Das from ISTS Kolkata, another guest of honor for the program. This is indeed a great pleasure for me to be the part of this valedictory function, as well as the part of the workshop program or the workshop, which was very nicely organized from the day 1 to the day last, and all the lectures were started in time and given sufficient time, what I have observed, for the question answer session as well as a doubtful to clear the doubt. And therefore, I will congratulate the Department of Physics, Assam University, Silchar, for organizing this wonderful workshop. I have observed that the topics covered in the workshop is right from the developmental part of the density functional theory to application, and of course the use of a particular code, that is quantum espresso. So therefore it is a complete package for the student, and that too was covered in the 5 days. So really this is an excellent job from the part of the organizers. And as far as the workshop is concerned, right, so density functional theory we have been hearing from last 5 days, and as you all know, it's a field which is growing up very fastly. Not only that, a lot of people work in this area, and this has become an essential part of the science, right? That means including physics, material science, chemistry, and all other things. Whether you do in the experimental research, you are in the experimental research or in the theoretical research, this has become essential, because when you have the experimental research, then to understand this DFT support is very much important. And if you are doing DFT alone, then also is very much helpful in predicting or modeling the new materials for the different applications. And applications have been discussed in your workshop very nicely from many speakers. And in fact, some modeling part was also discussed or described, and then of course the application. But what I would like to emphasize, the workshop has, in fact, it could accommodate some lectures on the developmental part. That means a theoretical part of the density functional theory, and that helps a student not only to understand that what is happening in the code, because many times students just want to know that how to use the code and how to get the result, and of course finally publish the result, but without knowing into the details that how the parameters are working, why they are working, how they have been done. And in fact, a workshop of this kind also helps one to understand that how the development of the field has taken place, right? If in fact, my topic was for the workshop as foundation, but if you remember, you all, that is in the first lecture of the workshop, Professor Sen, in half an hour, he in fact explained us very nicely the whole development of density functional theory. That is how it started and where it came. And of course, he also took on the basic or the most important part of the DFT, that Weinberg-Pohn theorem. And I try to cover that all the foundation part from the beginning to maybe to the application, and some uh, middle way things, that is whatever required for this. So I am always in the view that this kind of workshop should be arranged mainly to have the acquaintance to the students regarding the theoretical background of the subject, theoretical background of the code which they are using, because then only they can understand that how that will be going, that how basically you can play with the your code, what you are doing, you can understand. And in this regard, I'm really very much sure that the workshop has been very successful for the purpose, and that organizers have planned, decided to go ahead, right? And this is what from my side. I am really thankful to the organizers for giving me both opportunities. That means to deliver the talk as well as to be the part of this valedictory function for a very good, very successful workshop. So thank you very much. Um, Thank you once again.
Thank you, sir. Thank you so much for your suggestion. We'll surely try to take up your suggestions and good words, sir. Thank you so much. Now, I would like to request our guest of honor, Professor Abhijit K. Das, IACS Kolkata, to speak a few words. Sir, please.
Yeah. First of all, I would like to thank the organizer, Professor Shukla and others, to give the opportunity to share some of my works with you. And this conference indeed very successful in the sense that this is particularly for the hands-on session, and this is very important, particularly for the students who are try to learn and understand the subject, particularly the how to put the keywords and get the result, and to interpret the result on the basis of science. And this particularly hands-on session is very useful for the student. In other sense, that it is not like a black box. Normally, the student wants this program as a black box. They do not know much about what they are put as a keyword and what they are getting. But if some expert like Professor Jha, Professor Mishra, if these two good research workers and give some idea about how to use programs and what to interact to Professor Jha, Professor Mishra, and others to how to tackle their problem. So from this also they can get an idea about how to tackle their problem, and if there any mistake they do in the execution of the program, then they can take help from Professor Jha and Professor Mishra. And so in that way the conference is very successful, and I think this such type of conference will Professor Shukla and others will organize in future, particularly for the benefit of the students. And I would like thank you all, and this is a very very successful one. Thank you.
Thank you, sir. Thank you so much for your good words. Now, I would like to request Dr. Abhishek K. Mishra, Associate Professor, UPS Dehradun, to share a few words with us. Sir, please.
Thank the organizers, including specifically Dr. for this workshop. And this was really great pleasure to give Srini Professor and guiding the young minds as well.
Dr. Misra, there is some problem with your audio. Yes, no,
So is it not coming, Dr. Shukla?
no, we did not hear. Sir. Now it is okay.
Yeah.
Yeah. So I thank you, Dr. Shukla, and the organizers for giving me a chance to speak on DFT applications. And it was a really indeed a great pleasure to speak among the eminent scientists like Professor Sen and Professor Jha. And I echo with Professor Jha that we should be having next workshop where we have a specific section where we demonstrate how these codes have implemented the actual DFT. Yeah, that's it. Thank you again, the organizer.
Thank you so much, sir. Now, I would like to open the platform to the participants to share their views. Anyone from the participant sides, if anyone want to share their experience,
Yes,
kindly.
Gulab Sadi. Yes, Gulab Sadi.
Yes, Mr. Amit, I can hear you.
With your permission, I would like to speak a few words about my experience and what I have learned from this workshop.
Yes, sure. Go ahead, please.
So, good evening to everyone. My name is Amit, and I am a third sem MSc student from Assam University. To be honest, before this workshop, I had no idea about what is DFT. But thanks to this workshop, I got the opportunity to attend very nice lectures from distinguished speakers, starting from the very basics of density functional theory. I also got an insight of its various applications in various fields. So it was really beneficial for me to get an exposure to various research works and research works on DFT during this 5 days program. This basically gives me an understanding about how a research is done using DFT and in general what skills one should develop for doing research. Like one should be able to properly analyze the data and extract the helpful information out of it. Also, there will be numerous obstacles during our work, but one should keep patience and determination to complete the work. Additionally, I noticed that the computational physics plays a great role in visualizing and simplifying the models. And various new ideas and scope of DFT in future works were discussed. All this motivates me to also work in this field. So overall, this workshop has been very really helpful for me, and I would like to thank the organizing committee of this workshop and to all the speakers for their effort to make this program successful during this pandemic situation. I'm looking forward to participate in more of such workshops in future. Thank you so much.
Thank you, Amit. Anybody else from the participant side?
Good evening to all of you. This is Priyanka. I also want to share my experience from this workshop. I seriously got a lot of information from this workshop. Like I am also working on the 2D materials transition like TMDCs, and I calculating the band structure using DFT, uh, and like phonon calculation, and I'm facing a lot of problems during my calculation, like because due to attending this session, I got a lot of information, and I'm trying to solving my issue, and I got some ideas how can do calculation and how can do work in my research work to solve my problems. Also, I got some idea how to work in quantum espresso during calculation, and also a lot of things I learned from this session. And thank you so much, sir, for organizing this session. Thank you so much.
Thank you, Ms. Priyanka. We can take one more from the participant side.
Yeah, Gulabsa Rituparna Hajarika has raised her hand. So you can call him. Rituparna Hajarika, you can
Ms. Rituparna Hajarika.
Yeah.
First of all, thank you organizers for allowing me to attend this very informative and very wonderful workshop. Thank to all the speakers. I have learned a lot. I am very new to Quantum Espresso, and from this workshop I have learned many things. So thank you, and I'm looking for more workshops on Quantum Espresso on DFT. So thank you.
Thank you so much, Ms. Rituparna Hajarika. So we move on to our next speaker. Now I would like to invite our chief guest of the event, Professor K.D. Shen, University of Hyderabad, to grace us by sharing his experience. Sir, please.
Oh, thank you, Gulabsha. Can I request Professor Shukla to?
Yes, sir. I'm doing this job.
So, Professor Bhattacharya, Professor Sharma, and Professor Shukla. It has been a wonderful experience to be a part of this workshop, and I really think that it was a very successful experiment, as has been vindicated by the young participants who actually made presentations before me. We should definitely have many more such things with special focus, and absolutely necessary for all of us to also learn about the programming aspects of the theory, where we can write our own subroutines and make use of some of our ideas which nobody else has actually, because if you are able to write the part of the code that you yourself are imagining that you should do, then you will be ahead of the others, and that is something very important. So learning the programming, in addition of course to these massive programs which one cannot write so quickly, but one should be able to attach, add on, or implement actually partly independent subroutines to do things that you want to do. That is something which is very important, and it will be highly beneficial. Now, in the remaining time that I have for my 5 minutes, I want to show this this particular plot here, which is taken from a very recent article on symptometry on the evolution of density functional theory. It actually talks about the volume of the density functional theory publications coming from various countries all over the world, and also it assesses its quality and makes some future projections possible. So here on the y-axis is number of publications per year, and on the x-axis is year-wise. The data is 5 years old because it has been taken from 2000 to 2016, and very interestingly, well, if you come to 2016, let's say, now it is much more. I mean, but I think you can safely add 1,000 for each of the contributions. But the main point is the following, and that is that so if you are at 2016, then the contribution from India is roughly about 2,000 papers in 1 year. So in 1 year, we had 2,000 publications coming out of this country, which is pretty good in the sense that we started rather late. Like we have very few contributions, let's say about 15 years, 16 years back, or now 20 years back. But then in 20 years, we have picked up, and we have actually surpassed Japan, which is supposed to be having Nobel laureates like Fuki and others, very active theoretical chemists. But then the point here is that one of the very interesting finding is that from 2016, in the last 5 years, so from 2011 to 2016, the slope of our contributions per year has increased by 5 times. Okay, we have registered a growth of 5 times between the last 5 years. I'm sorry, we have registered a growth of I'm not able to see the curve because of this. Okay, now, yeah. So I'll just repeat myself. In last 5 years, we have made a 10-fold increase in terms of number of publications. And that is something which is very important. And it is this rate of growth is same as the rate of growth of China, which is the highest one. It has surpassed, it has taken over USA around 2012. But then, of course, there is a manpower and there is too much of infrastructure development there. And we are also concentrating on those things. And hopefully in about coming 5 years, which I am very optimistic that we will be very close to the top 3 contributing people, because this Europe is all together. It is not one country, it's all together. So we will have to separate that. But nevertheless, the point is that we are actually getting into this at right time with the right thirst. And this is very, very good for the future of those who are interested in pursuing this area as the research research topic. Now, the reason I mentioned about this is that if you look at the Schrodinger's paper of 1927, in about another 5 years or 6 years, we will be having 100 years of the origin, or 100 years of introduction of quantum science or quantum physics or quantum theory. And this is the right time, therefore, that is the in around next 5 to 6 years, when we are coming to celebrate in 2027 the 100 years of quantum mechanics. It's the right time to show the world that we are there competing to be number 1, as we are already between the first 3 nations contributing to the advancement of this discipline through the density functional theory. So with these words, I wish you all the best. And I thank once again Dr. Shukla for organizing a very wonderful workshop. And I'm sure as long as there is an interest like this, certainly the growing interest, the workshops also will be increasing in frequencies. And we are all there to participate in that. We actually learn from you when you ask the questions. So please ask questions and participate interactively. So thank you very much.
Thank you, sir. Thank you so much for sharing those information with us, and thank you for being with us. So now I would like to request Professor C.R. Bhattacharjee, Dean School of Physical Sciences, to give his remarks. Sir, please.
Thank you, Gulab Shah. Good afternoon, rather good evening to all present in this valedictory function. For reasons beyond control, I could not be present in the inaugural program or other sessions in the workshop. We are due for NAC accreditation in just 2 days time. So a lot of works to be completed before that. So I regret for not being able to attend any of the session. I am also a keen student of this particular discipline of DFT. The 5 days online workshop on density functional theory and its application being organized by the physics department has come to successful conclusion. Major new directions are being explored at fundamental level. Theoretical considerations, once thought esoteric, are turning out to be vital for the construction of computational tools for chemists, physicists, and material scientists. In fact, the theme of the workshop is quite relevant and timely. I sincerely thank and express our indebtedness to the experts for this workshop, Professor Prafulla Kumar Jha, Maharaja Shivaji Rao University of Baroda, Professor Avijit Kumar Das, ISCS Kolkata, guest of honor in today's valedictory program, Professor Kalidas Sen from the University of Hyderabad, the chief guest of this valedictory program, for giving time and such rigorous lessons over these 4.5 days to the participants of these workshop. Esteemed resource persons, Dr. Abhishek Mishra, Dr. N.R. Jaina, and Dr. Tanushri Shah Dasgupta, we are grateful for sharing your expertise. I compliment the coordinator, Dr. P.K. Shukla, Professor B.I. Sharma, Head Department of Physics, for the extreme good organization of these very important workshop. And also I congratulate the faculty members, scholars, and students of this department. This workshop has actually sensitized students and scholars from across the country, particularly who are beginners in the field. A good number of inquisitive participants across the country I get to see have attended. Thank you all for making this workshop a great success. I can also see Professor S.N. Thakur from BHU being here, whom I have visited almost 35 years ago as a student at BHU. Regards, sir. I means no words to record my deepest appreciation for the physics department for continued academic engagement through popular lectures on science, motivation, and webinars on thematic topics during the pandemic period. The scholars too have played a significant role in this regard. Organizational skills apart, the department is also known for the connect it has with national and international experts of various fields. Needless to say, during the course of last several years, I have noted that the faculties in the department has utilized profitably their own connection with peers in the field and has been very successful in getting eminent researchers and experts on board to deliver lectures. This workshop is also no exception. The enthusiasm it has generated by the discourse of the experts will not only enrich the knowledge base of the participants, but also trigger them for taking up modern research using DFT as a tool. As synthetic chemists, we in our group also use DFT as a tool through collaborative ventures to understand optimized geometry of complex molecules and other related ground state properties. We are amazed at the precise information such tools are able to provide us for the newly synthesized molecules, a thing we would not have dreamt of doing this through some laboratory experiments. The comments of the participants, which I can see in the chat box as well as in the audio, speaks volumes of the quality of the workshop, which has just come to a conclusion today. And this has been possible due to tireless effort of the coordinator, Dr. Shukla, with strong departmental support. We, as a university, are evolving slowly to achieve a benchmark quality, and with the radical changes of NEP being implemented, I will earnestly request the experts to help us in future also to raise the bar of both teaching and research in this university. And I look forward to your continued cooperation and assistance in this regard. Congratulations to all the participants and also to the organizer for this successful conclusion of the program. Thank you all. Jai Hind. Thank you. Regards. Namaskar.
Thank you so much, sir. Thank you for your valuable remarks, and you never fail to motivate us with your words. So thank you again, sir. Before proceeding towards the end, I would like to request everyone to kindly turn your camera on for the group photo. Kindly turn your camera on. We are going to click the group photograph, virtual group photograph.
Kindly turn on your video. Yeah. Yeah. Just capture कर लेना. Thank you, everyone.
Thank you, everyone. So now I would like to request Dr. P.K. Shukla, coordinator of the workshop, to propose vote of thanks. So please.
Yeah. Thank you, Gulab respected Dean, School of Physical Sciences, Assam University, and patron of this workshop, Professor C.R. Bhattacharya. Today's chief guest, eminent scientist, Honorable Professor K.D. Sen. Guests of honor, respected Professor Prafull K. Jha and Professor Abhijit K. Das. Invited speaker, Dr. Abhishek Misra. Head Department of Physics, Professor B. Najit Sharma. Colleagues and my dear participants, it's a matter of great pleasure and privilege for me to express my warm and sincere thanks on behalf of the organizing committee and my own behalf to all of you for your gracious presence in this valedictory function of the 5 days virtual workshop on density functional theory and its application. We are pleased to be able to organize this workshop satisfactorily, but this workshop would not have been possible without the help and support of many people. In the first place, I like to express our deep sense of gratitude and appreciation to today's chief guest, Honorable Professor K.D. Sen, for your kind support. Sir, you were the first person who I approached for organizing a course on DFT for our students and other interested researchers. And then after getting your big yes, I initiated the process of organizing this workshop. I like to add here that in spite of being a great scientist bestowed with several awards and recognitions, he was very kind in accepting all my requests for this workshop. His favor for Assam University is also reflected from his gestures. When he joined this workshop on very first day, he had kept with him Assam University Uttariya, with which we had welcomed him 4 years ago in 2017 in a national conference on chemical physics. Sir, we are very much thankful to you for your respect and love for the Assam University. Sir, I wholeheartedly thank you once again for your kind support in organizing this event. I like to extend my heartfelt thanks to today's guests of honor, Professor Prafull K. Jha and Professor Abhijit K. Das, invited speakers, Dr. Abhishek Misra, Professor Tanushri Saha Das Gupta, Dr. N.R. Jena for unreservedly accepting our invitation to deliver lectures in this workshop. I can say that I received the acceptance from Professor Jha and Professor Das within an hour. That was very surprising to me that I have just written and I got the acceptance. Thank you very much, sir, for accepting and giving us the giving the lecture for our participants. Thank you very much. I am also grateful to Professor Jha and Professor Das for sparing their valuable time for joining this validatory function. We hope that our esteemed speakers will extend their kind support in our future academic pursuits as well. Now, I'd like to express my sincere thanks to our Honorable Vice Chancellor, Professor Dilip Chandranath, and respected Dean Professor C.R. Bhattacharya for their administrative support and motivation. I gratefully acknowledge the constant support received from our head of the department, Professor B.I. Sharma, in organizing this workshop. I would like to thank all my colleagues, including Dr. Himadi Sekhar Das, Dr. Sarkar, Dr. Baro, Professor Desmukhya, and Biswasji, who extended their unconditional support in organizing this workshop. I would like to record my appreciation for our beloved research scholar, Mr. Bhaskar Goswami, who took all the pains for broadcasting the program live on YouTube, and Ms. Gulabsa for comparing the program. Last but not least, I'd like to sincerely thank the many stakeholders, our dear participants, for their active participations and for maintaining proper decorum while attending the lectures. It's online, so it was difficult. So thank you once again, the participants. I close here by thanking you all once more. Jai.
Thank you, sir. Thank you so much. Sir, am I audible?
Yes.
Okay. So before concluding the session, I request everyone to kindly stand up for national anthem, and kindly do not turn on your microphone as the audio doesn't sync, so it becomes difficult to cope up. You can keep your video on.
I'm sorry. I was disconnected, right, Gulab sir?
Yes, sir. Yes, sir.
Okay, so let me continue again. Sorry for the network problem. It never happened, but it happened in the last.
That's okay, sir. Sir, I requested everyone to kindly stand up for the national anthem. So, जन गण मन अधिनायक जय है भारत भाग्य विधाता पंजाब गुजरात मराठा विंध्य हिमाचल यमुना उच्छल जलधि तरंगा तब शुभ नामे जागे तब शुभ आगे गाहे तब जय गाथा जन गण मंगलदायक जय भारत विधाता जय Thank you, everyone. We hope to see you soon in another conference. Till then, stay home, stay safe, and take care. Thank you. Over to you, sir.
Yeah, thank you once again, everyone. I'm sorry I lost the connection in the last day. So it never happened. Thank you very much. And we hope that we will get your cooperation and support in the future as well. Thank you very much. Thank you, everyone.
Thank you.
Bye.
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 Thank you so much, sir. Thank you all.
You're welcome. All the best.
Thank you very much.
Sir, we can leave now?
Yes, yes, yes. We will share the.
Suklaji.
Yes, yes. Yes.
So, if,
Actually, I think Dr. Abhishek Mishra is not here. So,
okay.
yeah, I don't think he in the people list.
So, Shukla sir, I'm leaving now.
Okay, okay. Thank you very much. Thank you.
Sir, please inform me coming
Sri,
to Mumbai.
Pardon?
मुंबई आ रहे हैं तो बताइए कभी भी.
अरे वाह सर, थैंक यू. ठीक है,
हाँ?
आएंगे तो जरूर मिलेंगे.
हाँ, मैं अपना नंबर शेयर करता हूँ आपके ईमेल आईडी पे.
Okay, okay. Sure, thank you.
हाँ सर.
Yeah.
Rituparna and Sri Aishwarya.
So the participants who are here, I forgot to mention you that please allow us 8 to 10 days in sending the certificate. I will write email. Just
yes sir, no issue. No issue for certificate, sir.
Sir, actually because there is a NAC committee in our university and we are busy in with that. So,
हमारे यहाँ भी सर है 23rd 24th को यूजीसी का विजिट है हमारे यूनिवर्सिटी में.
ठीक है, then you can understand the problem.
Yes, yes, I can understand. कालिदास सर गए लगता है शायद से.
हाँ हाँ हाँ. Thank you. Program is over. So thank you.
Okay sir.
Yeah, thank you. Okay, Santosh ji, bye.
So Rituparna and Sri Aishwarya and Pratik, you are requested to directly contact with Professor Mishra. He is a nice person. His email ID is also given. I hope is also be shared. If not, you will get all the answers. Sorry that we couldn't able to get all the questions, but actually it sometimes happen. But one of your question, Pratik.
Actually, just
question most probably if.
Utpalji, just let me add one thing. Yeah. Abhishek ji has just dropped me a message in WhatsApp that because his office is closing, and that's why he has to leave the office. So that's why he is disconnected.
Okay.
He was
Okay.
giving yeah.
Pratik, if you are here, then I'm seeing one participant, Dr. Mohanlal Verma. Okay.
Yes.
He is also an expert. He can give the answer, I hope, regarding your phonon calculations.
Yes, sir.
Dr. Verma, are you here?
No, sir. Dr. Verma has left.
Okay. So I request you to kindly send an email to Mr.
No, he is not here. He has left the meeting.
Yeah. So send the email, I hope. That will be the best
He has
possible
left the meeting.
Okay, sir. Thank you.
Okay, sir.
One person I think who can possibly answer, Dr. Tara Prasad. Dr. Tara Prasad, would you like to take the question? Maybe sir, it is end, so everyone has almost I think left. Maybe they are here, but they have left.
Yeah. So, sir. Sugla sir, I'm leaving.
कैसे हो गया तो मेरा
Shukla sir.